Hey guys, in this video, the lovely Mr. B is going to take you through the skills and the techniques you need for your WJEC Level 2 certificate in additional maths. When you're doing this, you can use the free revision guide in combination with this and tick off the skills as you are confident with them. If there's any bits that you're not confident in, if you identify any gaps in your knowledge, then you can click through and watch the individual video on that. Once you're a bit more confident with your skills, then over on my website there is the course for you where it will track your progress and take you through loads of questions. And in addition, there is also a massive workbook.
Indices, we have multiple rules to go through. So for our first rule, let's say we've got 3 to the power of 2 multiplied by 3 to the power of 4. Now the answer to this is 3 to the power of 6. So our first rule is, firstly, we have our base numbers. So in this case, our base numbers, 3's, and these have got to be the same. So when we generalize this rule, let's assign it a letter. So let's call it n. So we have n multiplied by another n. Then we have the powers. Now look at what's happening with just the powers. We have a 2, a 4 is equal to a 6. So we've multiplied together the same base, but with the powers, they're not the same. They're actually adding together. 2 plus 4 is 6. So the way we can generalize this, we can assign numbers to these. So let's call them A and B. And that is going to be equal to those two numbers being added together. So our final answer would be n to the power of A plus B. So shortcut, if you're multiplying your powers, then you add them. For our next example, we could have 4 to the power of 8 divided by 4 to the power of 5. And that would equal 4 to the power of 3. So what's happening here? Now, again, the base numbers are the same. We've got 4 and we're dividing it by another 4. So these numbers can't change. You'll notice a different number to the previous example. So they can be any numbers you like. They could even be letters. So we generalize this rule, got an n, and we're dividing it by another n, another number. Now, let's have a look at what's happening with only the powers. So we have an 8, a 5, and it equals a 3. Now, 8 take away 5 is 3, and that's what's happening here. So when we generalize this, we've got the A and the B for our powers. So in the answer, it's going to be A take away B. The shortcut being, if you're dividing with your powers, then you just take them away. For our next example, let's have 5 to the power of 2. And then this one's going to be in brackets, and there's going to be another power on the outside of the brackets. And let's have this be a 4. So what's this going to equal? Well, it's going to equal 5 to the power of 8. So again, let's have a look at what's happening. Now, in this case, we only have one base number in the brackets. So when we generalize, we only have one to work with. Now, let's have a look at just the powers. So we have a 2, a 4, and then an 8. So what maths we get us there? Well, 2 times 4 is 8. So when we generalize, it ends in a bracket. We'll give our two powers letters. Let's call them A and B again. One inside the bracket, one outside. So for our answer, it's going to be A times B. And again, the shortcut is easy bracket. Then you're going to be multiplying the powers. Now you can see that we've got addition, subtraction, and multiplication rules. So do we have a division rule where n is going to be A divided by B? And we do, this does exist. So let's have a look at an example. So let's say we've got 7 to the power of 3, and the whole thing is being square rooted. Now the answer to that is going to be 7 to the power of 3 over 2, or 7 to the power of 1.5. And fractions mean the same thing as division. So to get the division, you need to have a square root involved. When we generalize this, again, we're going to have our n number, our base number, the kind of whole number in this situation. They can be decimals as well, actually. And again, this one's essentially going to be in brackets, but rather than being just normal brackets, they're going to be in a square root. Now, let's have a look at the powers. Now, you'll notice there's no 2. You have the 3. And the 3 stayed the same. Where's the 2 coming from? Well, the 2 comes from the order of which you're rooting. This is a square root, so it's a 2, because the symbol for square is 2. If it was, say, a cube root, you'd have a little 3 next to the root, and then it'll be 3 over 3 for this question. The denominator will be 3. So our A is the power of the root, and if it has no power, it's 2, and A is the power on our base number. Now, these are the four main rules, but there's other rules we can derive from this. Let's have a look at a little pattern here to see these rules. Let's say we've got 2 to the power of 3. That means 2 times 2 times 2, it's 3 2's multiplied together, which is 8. Then let's look at 2 to the power of 2. That's 2 2's multiplied together, that's 4. So far this is pretty easy, but what about something like 2 to the power of 1? Or 2 to the power of 0. How can we figure these out? Well, if you think about 2 to the power of 3 as 3 2's multiplied, and 2 to the power of 2 as 2 2's multiplied, then 2 to the power of 1 will be 1 2 multiplied. If you've got 1 2, you can't multiply it by anything, you've only got 1 2. So you can write down 2. Another piece of evidence for this is looking at the pattern. 8 divided by 2 is 4. 4 divided by 2 is 2. And then 2 divided by 2 is 1. So you can go through this pattern dividing by 2. And if there's not enough evidence for you, you can think about, well, 2 to the power of 4 will be 16. 2 times 2 times 2 times 2. So 16 divided by 2 is 8, and 8 divided by 2 is 4. So this sequence is a divide by 2 sequence. And so we get the odd results of something to the power of 1 is itself, and something to the power of 0 is 1. What if we continued? What if we had 2 to the power of -1 and 2 to the power of -2? Well, we'd follow the same sequence. We divide by 2 each time. 1 divided by 2 is a half, and a half divided by 2 is a quarter. Now, look at the pattern with the divisions. We've got a 1 as the numerator, but the denominator, we've got 2 and 4. Now, where have we seen 2 and 4 again? Well, 2 to the power of 1 is 2. 2 to the power of -1 is 1 over 2. Same number. 2 to the power of 2 is 4. So 2 to the power of -2 is 1 over 4. So let's say I wanted 2 to the power of -3, then that would be 1 over 8. So we can see patterns within this. Now, if we look at negative numbers, what about fractions? So if we had 2 to the power of a half, that's kind of working backwards from our fourth law of indices. So we've got a 1 divided by a 2. And the 2 corresponds to it being a square root. So 2 to the power of half is a square root of 2. Then we increase that. 2 to the power of a third would be the cube root of 2. So again, notice how if it's a square, we don't write the power on the root. We just assume that it's a 2. Now, the last thing to mention is that what if we had something like n plus an n, and we had a power on each, an a and a b? What would be the rule for that? Now, with addition and also with subtraction as well, because subtraction is the opposite of division, there is going to be actually no rule for that. So if you did get something like that, what you'd have to do is find the actual value, because all these things are shortcuts. But, look at our examples. We've got 3 to the power of 6, 4 to the power of 3. You can actually work out a large number for these. So, for example, 3 to the power of 6 in our first example is 729. So it's a fairly short number, but still 3 to the power of 6 is a shorter way of writing it. But when you get to addition and subtraction, there isn't a way to shorten the way you write it. So you just have to work it out. And then maybe if you're lucky, the answer you get as your value, maybe that would then be the product of a different, unrelated set of indices. And studying to write it twice, in my little list of formulas, with the no rule one at the top, I've written the plus minus symbol. Now, that's not some new kind of maths. That just means that either adding or subtracting is going to be the same. There's no rule. Now, one other thing I want to do, I just want to generalize the kind of the other laws column. So the key thing to take away from that is if you have n to the power of 1, then that's going to give you an answer of 1. So it's going to give you an answer of the number itself. If you have n and it's to the power of 0, then that's going to give you an answer of 1. If you have n and it's the power of a half, then that's going to be a square root of n. And if you have an n and it's a negative power, so let's say negative a for this, then that's going to give you as your answer 1 over that n to the a. So these are the kind of the key things you take away from that list of numbers. But as you can see, if you forget them, particularly the 1 and the 0 and the -1, you can derive those by looking at the pattern. And that pattern will work for any set of numbers. You don't need to do it with 2 like I did. If you forget the root one, then you can derive that from the fourth laws of indices, which was the one with the division. For surds, you can have some rules. So let's say we have the square root of a, and we add on the square root of b, then there is going to be no rule for that. Let's change the add symbol to a plus or minus symbol, because it doesn't matter if you're adding, there's no rule, and if you're subtracting, there's no rule. Where there is a rule is when you multiply. You've got the square root of a, and you multiply it by the square root of b. That's going to give you the square root of a times b, with both of them being underneath the kind of cap of the root. Alternatively, you can write it as the square root of ab. Same thing with division. If you have the square root of a divided by the square root of b, then that's going to be the square root of a divided by b, all under the same root symbol, which alternatively can be written as a fraction, the square root of a over b. Let's look at some examples. So let's say we had the square root of 9 plus the square root of 4. Like I said, there's no rule for this. However, we can do the square roots. Square root of 9 is going to give us 3. And the square root of 4 is going to give us 2. And now we can add those together and get 5. So there is a situation where you would be adding these together. Now let's look at an example with multiplication. So let's say we had the square root of 2 multiplied by the square root of 18. Now we can't do those square roots. We can multiply them together to give us a square root of 36. Now we do know what the square root of 36 is. The square root of 36 is 6. So 6 would be an alternative answer to this. See the benefits of using these rules, because you might be able to change some of these roots into nice whole numbers by using these rules. It'd be a similar thing with division as well. Now, there's 3 main types of questions I want to look at with Surds that you might need to do. The first one is with brackets. You might have something like 2 plus the square root of 3 multiplied by 2 minus the square root of 3. Now, this is a quadratic question, so you'd use the methods used for quadratics, but you'd have to be careful that you also use the Surd rules at the same time. The 2 times the 2, which would give 4. You would do the 2 times a negative 3. So 2 times a negative root 3 would give you negative 2 lots of root 3. So you can't do it. The multiplication rule is only when both of them are roots. 2 isn't a root. So you can write 2 root 3. Then you would do the root 3 times the 2, and that gives a positive 2 root 3. And then the final one would be the root 3 times the root 3. Now, this is where we have to use the rules of the Surds here. A root 3 times a root 3, we can multiply those together to give root 9. And since we have a positive root 3 and a negative lot of root 3, then actually that's going to be a negative root 9. Now, we can simplify this actually. So we've got the 4, the negative 2 root 3, and the positive 2 root 3. We can add those together. And if we add them together, it's going to give us 0 root 3. So that's going to disappear. And we know what root 9 is. Root 9 is 3. It's a square number. Actually, it gives us 4 take away 3. And we can answer that. It's 1. So double brackets actually cancel out to give us 1. Now, it's going to be useful to go back to our list of Surds and add that rule in green. So what I'm going to do is, let's go back to the one with no rule because we don't need to remember this. So let's say we've got root A and we've got another root A and they are being added together. And the answer is also going to be a root A. What changes is the coefficient, the number on the root A. So let's say we had a B and a C on them. So I had B root A and C root A, then our answer would be B plus C root A. Let's put that in brackets actually to make sure we do that. So you can add roots, but it's in a very specific situation. And it's not like the multiplication and the division rules. It's quite different. So they've got to have the same base. Whereas when you multiply and divide, they don't need to have the same base under the root. Now, as well as brackets, which is kind of a multiplication, there's also kind of a division version of this called rationalizing the denominator. So let's say we've got something like 2 over root 3. Now, when you rationalize this, what we mean is we do not want a root as a denominator because that throws up problems. We do kind of more complicated kinds of maths. What we need to do in this situation is we take our 2 over root 3 and remember, with fractions, you can multiply and divide the top and the bottom by the same number to kind of simplify or find equivalent fractions. I'm going to exploit that fact here. So how do we get rid of a root 3? Well, what you're going to do is you're going to multiply it by itself. So we're going to multiply the denominator by root 3. We'll keep it the same fraction. We're going to multiply the numerator by root 3 as well. And what that leaves us with is, on the top for the numerator, 2 times root 3 is 2 root 3. But for the denominator, root 3 times root 3 is root 9. And we can do root 9. Root 9 is 3. So we're going to have 2 root 3, all being divided by 3. Now notice I wrote that in purple. Now look at all the purple examples here. This is where, and it's only going to be visual with the surds, if you ever see a square number underneath a root, it's usually beneficial to cancel it out into a whole number, because we can do root 9, it's 3, so why not do that? And now we've got a rationalized denominator. We have a whole number for the denominator. There's one more type of rationalizing that I need to show you. So let's say we've got 2 over, and then we've got 2 plus root 3. Now, if you tried to multiply all of that by root 3, this would happen. You'd have 2 root 3 for the numerator, well, that's fine. You'd be adding on 3, because root 3 times root 3 is root 9, which is 3. But then you'd also have to multiply the 2 in the denominator by root 3, and you have 2 root 3 on your denominator. Now, we still have a root on a denominator, so it's not been properly rationalized. So you can only multiply a root by itself if it's the only thing down there. What if you got something else down there? How do we get rid of the roots? Well, notice how I've got 2 root 3 as my denominator. Look at the brackets question. When 2 root 3 was multiplied by 2 minus root 3, when we multiplied out the quadratic, all of the roots cancelled out. So what you need to do in this situation, when you have multiple things for the denominator, is you take the 2, you take 2 plus root 3, it's helpful to put in brackets at this point, and we're going to multiply the bottom by 2 minus root 3. So it's the same numbers, but I flipped the sign. We do the same thing to the numerator. And we already know the answer to this. The answer to that denominator is the answer to our bracket example. It was over 1. That's what it all cancelled down to. But you wouldn't necessarily have that in an exam, so you might have to actually multiply out the quadratic and get whatever answer it is. But it should be cancelling out to have no roots. And then the numerator, when we've simply got 2 lots of 2 minus root 3. So it's kind of okay to write it like that, actually, but you might want to multiply out the brackets and multiply both parts by 2. So let's do that. So 2 times 2 is 4, and 2 times negative root 3 is negative 2 root 3. Now, sometimes your answer will look like that, but in this situation, we can actually deal with the denominator. The denominator is a 1, and if you divide by 1, it's going to stay the same. So we can actually get rid of the denominator in this case. But you will sometimes have a denominator. Another thing you could do, if the denominator ended up being a 2, you can still get rid of it, because you can divide the 4 and the negative 2 by 2, and you can simplify the numerator. So always look for opportunities to cancel down. But again, you will sometimes have a denominator here if you can't cancel. But in this case, we could. Changing the subject of a formula uses the same principles as solving equations. So let's say we have y is equal to 11x minus 4. If we were solving the equation, what we would do is try and get x on its own, and we would add 4 to both sides. And that's what we do. And that gives us y plus 4 is equal to 11x. Now, when you're solving an equation, in the position of a y, you would typically have a number that you can add 4 onto. Now, in this situation, we've got a y there, so we can't add 4 onto it. So just leave it as y plus 4. When we now do the next step, and we need to divide both sides by 11 to get x on its own on the right-hand side, again, typically the y plus 4 position would have a number that we can divide by 11. In this case, we don't have that. So how can we do it? Well, all you do is you write down y plus 4 again, and then you make it into a fraction with 11 as the denominator. And what this does is it shows that you're attempting to divide by 11, but at this time you are unable to divide by 11 because you don't have a value for y. And so this is the essence of how you change the subject, because now we have an x equals, and now we have a formula to find x, whereas we started off with just a formula to find y. So let's have x take away 9, and all of that is going to be squared, and it's equal to y. So again, we want to get x on its own. So we have to kind of unwrap the layers of mathematics around x to get it on its own. Outermost layer is the squared symbol, so we need to root both sides. That will leave us with x minus 9 on the left-hand side, and then we're going to have to square root the y. Once we've done that, we can add 9 to both sides, and we get x is equal to the square root of y plus 9. And again, typically here, y would be a number that you can square root. And then that'll give you a number that you can add 9 to and get a value for x. But when we change the subject, our answer is going to be another formula. So we started off with a formula to find y, and now we have a formula to find x. Let's look at something with a few more steps. So we've got 5x plus 2y, all divided by 5, is equal to 7. So again, we get x on its own, and we have to kind of unwrap all the layers around it. The outermost layer being the divide by 5. So we multiply both sides by 5, and that moves the 5 over to the right-hand side. 7 times 5 is 35. So in this case, there is actually some maths we can do. We can do 7 times 5. So it's not always going to be maths that you can't do. Next, we can take 2y away from both sides. And finally, we want to divide through by 5. We have x is equal to, and then we're going to have 35 minus 2y, and we're dividing all of that by 5. And note that I said we're dividing it by 5, but I haven't actually divided it by 5. Because while we could divide the 35 by 5 and get 7, we can't divide the 2 by 5. You could actually do something here. So we could do 35 divided by 5 is 7. Then we could do 2 divided by 5 is 2/5. So actually, this could actually be a simpler form. So both of these outcomes are fine. It's just depending on if you want, a large division, a large fraction, or if you want a smaller fraction involved in this. And again, note with the 2 divided by 5, I couldn't do 2 divided by 5, so I just wrote it as a fraction. I'm indicating that I want to do 2 divided by 5, but I can't at this time. Let's look at one last example. So we're going to have 10 plus 14x all over xy, and that's equal to 7. So for this question, the change here is that sometimes you are going to get multiple sets of the thing we're change the subject to. Unwrap some layers here. So let's multiply both sides by xy. And that will give us 10y plus 14x is equal to 7 times xy. And our aim here, now we've done the fraction, we want to get x on its own. We have 2 sets of x's. So we need to get the x's onto the same side. So what we could do is we could take away the 14x from both sides, and that will give us 10y is equal to 7xy, take away 14x. And once you've got all the x's to the same side, what you want to do now is factorize both x terms to get a single x. So both of the terms with an x in, they've both got an x, but they've also both got a 7, because we've got 7x and we've got 14x. So we've got a number factor as well. So we take 7x outside of brackets, then we divide through by 7x. 7xy divided by 7x will leave us with just y. And 14x divided by 7x, 14 divided by 7 is 2, and x divided by x means we're multiplying by 1. And so there's our next line. So by factorizing, we now only have one x. What we can do now is we can divide both sides by the bracket, and that will mean that the bracket is going to be dividing the 10y now, and that's going to be equal to 7x. Now, at this point, what we also want to do is get rid of the 7 on the x, and we'll be dividing that as well. So we've already divided, and we've got another divide to do. All we need to do is add the 7 to the denominator as well. So the 7 is going to join the denominator, but it's going to be multiplying the things that are already there. And there's our answer. The last thing you might want to do, you could expand the brackets if you prefer to. That's something you could do. So we could have 10y over 7 times y, and 7 times negative 2 is equal to x. So there we have 3 examples of taking the subject. And again, it's exactly the same as solving an equation. It's just sometimes you won't actually be able to simplify it at various points. And so you'll leave divisions as fractions, for example. With factorization, you should be familiar with kind of single bracket factorization. We might have something like 4x plus 20. And when you factorize it, you think about what the highest common factor of the 2 numbers are. So we've got 4 and 20. And so the highest common factor of those is going to be the 4. And you remove that outside of a single bracket. Inside the bracket is going to be the result of dividing your expression by 4. So 4x divided by 4 is 1x, and 20 divided by 4 is 5. This is something that you should already be confident with. What we're going to focus on with this bit of revision is quadratic factorization. So you might have something like x squared plus 9x plus 18, and be asked to factorize it into a set of brackets. So how would you do that? Well, the key thing is that you want two numbers inside these brackets that add together to make the 9, and they multiply together to make the 18. Now, you might be able to figure that out just by looking at it, but there's a method if you can't. So what you do is you take the 18, the number you need to multiply for, and you list all the possible options of numbers that multiply together to make 18. So you can have 1 times 18, 2 times 9, 3 times 6. We can't divide it by 4 or 5. We can divide it by 6, so we finished our list. So note how I did that. I divided it by 1, wrote down the answer. Divided by 2, wrote down the answer. Divided by 3, wrote out the answer. Tried 4 and 5, they didn't work. And then when I repeated myself with 6, I knew that the list was complete. So what we need to do now is think, well, which ones of those numbers are going to add together to give 9? You have a look through, you'll see that 3 and 6 make 9. So what do you write in the brackets? Well, we need an x in both because we need to have x times x is x squared. Then we're simply going to write in the 3 and the 6 in either order, it doesn't matter, and they were being added on. They're positive numbers, we're going to write an add symbol. And that's it, we've factorised the quadratic. So let's look at some harder ones. Next, we're going to look at x squared plus 4x take away 32. So we're going to have some negative numbers here as well. Now, we still want two numbers which add together to make 4 and multiply together to make 32. So you write a list of factors with 32. You can divide it by 1. We can divide it by 2. We can't divide by 3. We can divide by 4. We can't divide by 5 or 6 or 7. And we can divide it by 8. We've already got 8 written down, so we must have finished our list. So we look through the list and we think, right, which of these numbers add together to make 4? And at first glance, none of them will add together to make 4. So we know we write the x in the brackets. What else do we write in? Well, because the multiplication is a negative, it's a negative 32, we are allowed to use negative numbers. So when you look through the list, you think, well, if I'm allowed to take away, how could I get a 4? So 1 and 32, you could get, you could get 33, you could get 31, you could get, negative 31 or 33, depending on these negatives or not. So that's not going to help us. We can eliminate that one. 2 and 16, we can add them to get 18. We could take them away to get a 14. That's not going to help us. And 4 and 8, we can add them for 12. We take them away. 4 take away 8 is negative 4. Well, this looks promising. What about the other way around? 8 take away 4 is 4. And so we found our answer. So we write in the 4 and the 8. Again, in either order. It doesn't matter which way around they are. What does matter is the way around the negative numbers are. And you think very carefully about how you got a positive 4. And it'd have to be a positive 8 and a negative 4. 8 take away 4 is 4. So in the brackets, we need a positive 8 and a negative 4. So always be looking out for negative numbers as well, if you can see it in the question. And be thinking about takeaways. When we talk about, two numbers that add together to make the middle term, we are allowed to take them away as well, or have any kind of combination of negative numbers that you need. Lastly, we'll look at two special cases. So what if we had x squared take away 9? So we're thinking, I need two numbers, that multiply together, or two numbers that, multiply. When you look at this, there's only one number. So, is this going to be an adding or a multiplication number? So if we look back at the previous questions, the numbers you have to add always have an x on. And the numbers that you have to multiply are just numbers. So it's going to be two numbers that multiply together to make 9. But what about the addition bit? Now, it is actually there and it's hidden. So x squared minus 9 is the same as saying x squared plus 0x minus 9. And so you want two numbers that multiply together to make negative 9, but they add together to give 0. That's what it means. So when you have your double brackets, there's only going to be one option for something like this. And it's going to have to be the same number twice. So to get 9, what's the same number twice that gets 9? It's going to be 3 and 3. So it's a square number, and there's a missing term. Just kind of square root it. And it's going to have to be a positive 3 and a negative 3. And then what's going to happen is, when you add those two numbers together, 3 and a negative 3 will make the 0 for you. One other special case is, rather than having the addition part missing, the x term missing, you might have the multiplication term missing. So you might have something like x squared minus x. Now, in that situation, this isn't going to be a quadratic because you want two numbers that multiply together to make 0. So what that means is one of the brackets is going to be a 0. So when you have your double brackets, it's going to act like a linear kind of factorization. So you see you've got an x in both. So we take out the x, and then we divide both by x. So x squared divided by x is x. Negative x divided by x is going to be -1. And that's going to be our answer. Again, coming back to, want two numbers that multiply together to make 0 and add together to make -x, -1. One of the brackets is missing. The x on the outside doesn't have a number with it, and that's how you get the 0, because effectively it's x plus 0. However, rather than overthinking it, just treat questions like this with a missing number on the end as a linear factorization. Now, the next stage of difficulty after this is something like 4x squared minus 18x plus 14. And with this one, when you open up your double brackets, before we were writing x and x, because x times x gives us our x squared. However, with this question, it's not an x squared, it's a 4x squared. So you could have 4x times x, or you could have 2x times 2x. So it's going to be one of these two alternatives, and you don't know which one it's going to be. So that's the first difficulty. The second difficulty is when we look at factors for two numbers that multiply together to make 14. So look at the factor list for 14. We can divide it by 1, and we can divide it by 2, and we can't divide it by 3, 4, 5, or 6. So these are the only possible factors. Now, we need to add or subtract these to get a -18. And these numbers are all too small. You are not going to be able to get a -18 out of these numbers. So what on earth do you do? Well, you are allowed to multiply by the coefficients on the x. Because when you expand the brackets, these numbers are going to get involved. So if it's the first alternative and it's 4x times x, you can multiply one of the numbers by 4, and you can multiply one of the numbers by 1. And this will give us a fresh list of alternatives. So we could have 4 and 14 if we multiply the first number by 4 and the second number by 1. Or we could have 1 and then 14 times 4, which is 56. Same thing with the 2 and the 7. We could multiply the 2 by 4 to get 8 and the 7 by 1. Or we could multiply the 2 by 1 and the 7 by 4 to get 28. So we've got a larger list of possibilities. So this is our 4 and 1 list. Let's just box it off. Let's make a list for 2 and 2. So we can multiply the 1 by 2 and the 14 by 2. Or we could multiply the 2 by 2 and the 7 by 2. And since they're both the same, you can't do it the opposite way around because it'll just give you the same answer. So we've only got two alternatives for the 2 and 2 option. So what we need to do now is look through this list and think, well, which ones of these could make 18? So 4 and 14 can. 8 and 7 are going to make 15 together. That's not going to work. 1 and 56, that's way too big. 2 and 28, I mean, we could take away the 2 to get 26, but that's still too big. 2 and 28, we do a take away, we get 26, that's too big. And 4 and 14, again, from a different method, that could also give us the 18. So now we're going to think about which one it's going to be. Now we want to add them together to get a -18. So it'd have to be a -14 and a -4 in both cases. Now, when we write these into the brackets, we don't write the 4 and 14. We write the original numbers they came from. So it's going to be the 1 and the 14. You're going to think really carefully about which way around they are. Now, the 14 stayed as it is. So that's going to go in the bracket with the 4. And the 4, the 1 was multiplied by 4 to get 4. So the 1's going to be in the opposite bracket to the 4. Because when you multiply this out, to get that 1 multiplied by 4, it can't be in the same bracket as it. So we've got that the correct way around. And then, of course, in the second alternative, because they're both being multiplied by 2, it doesn't matter which way around they're going to be. Now, the second alternative is multiplied from the 2 and the 7, multiplying them both by 2. So we're going to have the 2 and the 7 in for that alternative. So now we're going to think, well, how do we get a -18? Well, they've both got to be negative. And so now we've got two possible answers. This is actually quite unusual to get two possible answers. But there we are, we've got two alternatives. There's two different ways to factorize it, and whichever one you use depends on what's going to happen next. If the question is just to factorize, either one will be a correct answer and you'll get full marks. If you need to do something else afterwards, then there'll be some kind of clue as to which of these two is going to be the most relevant. Which brings us on to the next thing we'll look at. So you could get something like this. You can have x squared plus x minus 20 all over x minus 4. Now, in a question like this, what you're going to do is factorize what you can. And you can factorize the quadratic on the top row. Now, I'm not going to go through this in detail because we've already revised that. So the answer to the factorization is going to be x plus 5 and x minus 4. And what you'll notice is that one of the factors is the same as the denominator of the fraction. So all you need to do is divide them by each other. If you divide a number by itself, you get 1. And if you multiply by 1, the answer stays the same. So effectively, by factorizing, we can actually cancel down the fraction. And the answer is x plus 5. Now, we can also do this with more complicated ones. So let's say we had 10x plus 15 all over 8x squared plus 4x minus 12. Now, normally, if we were going to do what we did with the 4x squared question earlier on, how many alternatives are there for 8x squared? Well, you could have 8 times 1, you could have 4 times 2. You know, there's a few different options there, and you're going to get like a long list of possibilities potentially. But there's a clue in the question. Because it's a fraction, you know that it's probably going to end up being cancelled down. Now, on the numerator, we've got 10x plus 15. Now, if we have 10x in a bracket, that's not going to multiply by anything to get 8x squared. But you can factorize it as a linear factorization. And the 10 and the 15 have got a common factor of 5. So you could write 5 and then 2x plus 3 in the brackets. Now, this is a clue that one of the factors is going to be 2x plus 3. And this is going to shorten down the list of possibilities that you have for this question, because you know you want to get a 2x plus 3. So we want to get a negative 12, for example, at the end by multiplying together the two numbers. So the only way to get a negative 12 is for the other factor to be negative 4. And then with the x's, we want to get 8x squared. We're going to multiply 2x by something to get 8x. So it must be a 4x. And what we can do is we can test it out and make sure it works. So maybe you can multiply it out to check. 4x times 2x is 8x squared. Negative 4 times 3 is a negative 12. 4x times 3 will give us 12x. And negative 4 times 2 will be negative 8. So 12 and negative 8 will give us that positive 4 in the middle. Looks like it works. So now all we need to do is divide the same factors by each other and cancel them out. What we're left by is 5 over 4x minus 4. And that's your final answer. And so you can see by having that clue in the question, it's a fraction, we're probably going to be simplifying the fraction. We could guess what one of the factors were going to be, and it shortened the calculation down for us to the point where we could do it in our head quite easily. With linear equations, you have to collect all of the x terms on one side and all the number terms on the other. So, for example, let's say we have 5x plus 10 is equal to 35. What we want to achieve here is have the x terms on one side and the number terms on the other side. So we have a value like x equals something. We're trying to find a value of the x. Now, the way that you solve these is through kind of patient, systematic, step-by-step changes to both sides of the equation. So, for example, with this one, we can take 10 away from both sides, and that leaves us with 5x is equal to 25. And so what we've done is we've made the equation simpler, but we haven't changed the values of anything in the equation because we did the same thing to both sides. Then our next step, we can divide both sides by 5, and that leaves us with x is equal to 5. And now we have the answer that we were looking for. Sometimes when solving an equation, you might have multiple values of x. So for example, you could have 5x minus 20 is equal to x minus 12. Now, in this situation, the first step should be to get all of the x values onto one side. So, for example, here, we could take x away from both sides. We're getting rid of the smallest value of x. And that will leave us with 5x take away x will give us 4x. So 4x minus 20 is equal to negative 12. Now we've done that, we can add 20 to both sides. And that will give us 4x is equal to a negative 12 plus 20 will be a positive 8. So now we divide both sides by 4, and that will give us that x is equal to 2. So the important things here are knowing which order to do each inverse operation and knowing what the inverse operations are. Generally, it's easier to get rid of plus and minus first, and then do multiply and divide. However, you need to be careful about things like fractions, square roots, brackets, powers, which may alter the order in which you need to do things. One way of solving equations, which makes things look very different, is when you have a quadratic with an equation. So, for example, we could have x squared, take away 14x plus 49 is equal to 0. Now, you should have already covered factorising quadratics. If you haven't, you need to go and revise that first, because I'm not going to go through it here. But essentially, when you factorise this, you'll get something like this, where we have x minus 7 and x minus 7 in brackets. And the difference between factorising quadratic and solving a quadratic equation is you just have this equal 0 on the end. What we don't have here is the kind of x equals a number we're looking for. But there is an easy shortcut we can use to do this. And what we want to look is, we want to make one of the brackets be equal to 0. Because if one of the brackets is equal to 0, then it's multiplying the other bracket by 0, and then you get 0. So how can we make the brackets equal to 0? Well, you have to look at the values of x. You have to think, what could x be to make each bracket be equal to 0? And you might get multiple options. So for the first bracket, highlighted in green, x would have to be 7 to make that bracket equal 0. You have 7 take away 7 is 0. So no matter what the second bracket is, you're always multiplying by 0 and you get 0. Highlighted in pink, the second bracket would also need to be 7 for everything to equal 0. And so for this one, we can see that x is just equal to 7. Now, why have I bothered to look at each bracket separately when they have the same answer? So let's look at another example. So let's look at x squared minus x minus 56 is equal to 0. Now, again, knowledge about factorising to factorise the quadratic part of this. And if you factorise the quadratic, what you should get is x minus 8 and x plus 7. So then again, we look at each bracket separately when you think, what could x be to make the bracket be equal to 0? Because then the other one doesn't matter, because you multiply by 0, you get 0. Well, for the first bracket, x would have to be 8, because then you get 8 take away 8 is 0. But for the second bracket, x would have to be equal to negative 7, because negative 7 plus 7 is 0. So we have two possible answers. So which one do we choose? Well, actually, all you need to do is say that x is equal to both of them. It's equal to 8 and it's equal to negative 7. The only time you have to choose between the two is if this was part of a practical question and a negative value will be impossible if the context is some kind of real-life problem. This method works even if you have something more complicated like a cubic. So let's say we had x cubed, or let's do 3x cubed, plus 27 x squared plus 72x plus 48 is equal to 0. Now, again, I'm not going to go through how to factorize this, but you're probably going to be using some form of algebraic long division to do it. But you're going to end up with values in 3 brackets and it'd be equal to 0. There's more than one option for this one, but you could have x plus 1, x plus 4, and 3x plus 12. So again, what you need to do is look at each value of x and think, what could this value be to make the entire bracket be equal to 0? So for the first x, it would have to be negative 1, because negative 1 plus 1 is equal to 0. The second one would have to be equal to negative 4, because negative 4 plus 4 is equal to 0. Then the third one's more complicated because it's taking the form of an equation. So we have 3x plus 12. So what we want is we want the 3x to be equal to negative 12 for it to equal 0. So sometimes a little more complicated to figure out what x is. And if 3x needs to be equal to negative 12, then 1x needs to be equal to negative 4. So now we've got all of our alternatives. We can write down our answer. And x we need to be equal to negative 1 or negative 4. And because two of the brackets have negative 4 as a value, we only need to write it down once. Just like with our first example like this, both brackets are equal to positive 7. So we can just write 7 as our answer. So only write down multiple options if they do take different values. Now, the last thing we'll do here is that with so much on the page, it might not be very clear which ones are the answers. I'm just going to highlight all the answers in purple now. The first example, x was 5. The second example, x was 2. In the third example, x was 7. In the fourth example, x was 8 or negative 7. And in the final example, x was equal to negative 1 or negative 4. Algebraic long division is all about factorising things that are larger than quadratic. So, for example, a cubic. So you might be given something like factorise, and you'd be given a cubic. So let's say x cubed minus 5x squared plus 8x minus 4. And you might be given a clue. So you might be told that one of the factors exists. So, for example, that x minus 1 is a factor. Alternatively, rather than full factorization, you might be asked to show that x minus 1 is a factor, but it's going to be the same maths. So what we do to solve this is do something called algebraic long division. So we set up a division. Now, with this division, we're going to have x minus 1 as a thing we're dividing by. And the thing that we're dividing is going to be the x cubed minus 5x squared plus 8x minus 4. You might be thinking, well, this looks horrific. You know, how on earth are we going to divide these? And we use a little bit of a trial and error, and we go step by step. Now, what we're going to do is we're going to focus on dividing by just the x, and we'll deal with the minus 1 after we've attempted dividing by x. So we're going to go through one term at a time. We're going to start off with the x cubed. We're going to divide x cubed by x, which gives us x squared. We're writing x squared. We're not going to write it in the first spot above the cube section. We're going to write it in the squared section. So our answer is going to go here. Now, once you have done that, what you need to do is then check that this is actually the right answer, because we didn't divide by x. We should have been dividing by x minus 1. So we kind of have to work backwards now and make sure we've done this correct. So we take our answer. I'm going to multiply it by the term at the start. So we're going to do x squared times x is x cubed. And we're going to do x squared times negative 1, which will be negative 1x squared. If we've got x squared as our answer, the part of the calculation we've dealt with is x cubed minus x squared. But there's still a lot of the calculation left to go. So what we do now is we work out how much of the calculation is left. And the way we do that is we are going to take the parts away. So we're going to do x cubed take away x cubed is 0. Then negative 5x squared take away a negative x squared, double negative there, so it'll be an add. Negative 5 plus a 1 will give us negative 4. So it'll be negative 4x squared. And then there's nothing to take away for the next two sections. They stay as they are. So this is the part that we've got left. And now all we do is we repeat the process. We're going to divide by just the x. So our next term is negative 4x squared. We're going to divide it by x, and that gives us negative 4x. We write that down in our answer. And then we're going to check that we've done it correctly. So we're going to bring that forward. I'm going to multiply it by the thing we're dividing by. So we're going to do negative 4x times x, which is negative 4x squared. And then negative 4x times negative 1, which will be a positive 4x. And then we check how much of the equation is left over by taking away. So negative 4x squared, take away negative 4x squared will cancel it to give you 0. 8x take away 4x is 4x. And there's nothing else to take away, so the minus 4 will stay as it is. And then we'll repeat the process again. So now we've got a 4x left over at the start. We divide that by x, and that gives us 4. So we write in 4. We bring that back to the front, and 4 times negative 1 is negative 4. We then check how much we've got left by taking them away, and you can see now that we're going to have 0 left over. So we have finished. And if you have 0, that proves that it's a factor. There's no remainder. We've completed it. If you got an answer that wasn't 0, that would be a remainder, and it means that what you have isn't going to be a factor. So now it's proven that x minus 1 is a factor. How do we factorize this? Well, we know that x minus 1 is a factor, and we know the answer to our division is a factor as well. So that's going to be x squared minus 4x plus 4. We know that that's also going to be a factor. So all we have to do now is take quadratic and factorize the quadratic as well. So you can do that using any method you like, but if you factorize the quadratic, which is something you should be more comfortable with, that should be x minus 2 in both. And now we've got our full factorization. So not only does the algebraic long division prove that something's a factor by having a remainder of 0, but it also will give you, for a cubic, it will give you a quadratic that you can then factorize for the rest of the factors. So now let's have a look at another example. So let's say we need to factorize x cubed, take away 5x squared, plus 3x, plus 9. And this time we are not going to be given a clue. So how can we factorize it? Well, a good thing to look at first is to think about the number at the end. We've got a 9 at the end, and it's cubic, so we're going to have 3 brackets. So we're going to think, well, which 3 numbers are going to multiply together to make the 9? And you don't have a lot of options, really, for some numbers. So if they're 9, you could have 3 times 3 times 1, for example. Now, that's not the full story, because we know we have a negative number in this, so we're factorising it. We're going to be getting a negative 5x squared. So some of these need to be negative. Now, given that 9 is a positive number, 2 of them are going to have to be negative. So then that gives us a lot more options. We can have negative 3 times negative 3 times 1. Or we could have 3 times negative 3 times negative 1, for example. So here are a few different alternatives. And, no matter which one you choose, you could be wrong. So if you can't figure out exactly which one's going to be correct using logic, you're just going to have to give something a go. So I'm going to have a go, and I'm going to use x being equal to 3. So we're going to set up another algebraic long division. We're going to divide through by x plus 3, and we're going to divide through the full number. So like we did with the previous question, we're going to divide through by just the number at the start, which is the x. Let's free up a little bit of space here. So we've got an educated guess. I'm going to guess that x plus 3 will be a factor. Let's check to see if it is. So take your first term, which is x cubed, and divide it by x. That gives us x squared. So we can write x squared in as the first part of our answer. Then we didn't take into account the plus 3, so we're going to bring that back to the start and check the plus 3. So we do x squared times x is x cubed, and x squared times 3, which will give us 3x squared. So we've not just dealt with the x cubed, we've dealt with an x cubed with a bit extra as well. But we need to see what's left over before we carry on. X cubed take away x cubed is 0. Negative 5x squared take away 3x squared will be a negative 8x squared. And the rest will stay as it is. So now repeat the process. Now at the front we have negative 8x squared. We're dividing that by x, and that will give us negative 8x. But then, of course, we haven't dealt with the plus 3, so we need to multiply that by our original number. So negative 8x times x is negative 8x squared. Notice how this always gives us the same number at the start. And then negative 8x times 3 will give us negative 24x. So we take away to see what's left over. So the first term always going to cancel out, and the next term, negative 3, take away a negative 24, double negative there, that will give us a positive 27, 27x. And we're adding 9 to it. That didn't change. So now we take the 27, we divide it by x, and that gives us 27 as our answer. So then we, again, multiply that by the start to see what we have left over. So 27 times x is 27x, and 27 times 3 is going to give us a 81. Then we take these away from each other. What's going to happen is we're going to have a remainder. We're going to have 9 take away 81, which gives us negative 72 as a remainder. Since we don't have 0 at the end, that means that x plus 3 is not a factor. And so we've guessed wrong here. And this might happen in exams. So if this happens, don't worry about it. Okay, we've done some working out. At least we've proven that we can do algebraic long division, even though it's not something that's helpful to us factorising this. So we've got a few marks already. So what we need to do now is we need to rub this out, and we need to try again. Now, I know that 3 definitely has to be factoring to this somehow to get that 9. So rather than being a positive 3, let's try a negative 3 instead. And let's see what this gives us. So we proceed the same way. We have x cubed at the front, and we're dividing it through by x, and that gives us x squared, which we can write in as our first answer. We haven't taken into account the negative 3, so we need to multiply that by the numbers at the start. X squared times x gives us x cubed, and x squared times negative 3 gives us negative 3x squared. So now we're going to see how much of the equation is left to do. So the first terms cancel out. Negative 5 take away a negative 3. It's a double negative, so we added negative 5 plus 3 will be negative 2. And the rest of it hasn't changed because there's nothing to take away from those two terms at the end. Then we'll repeat the process. Now at the front we have negative 2x squared. We're dividing 3 by x. That gives us negative 2x. Write that down as an answer, but multiply it by the numbers you're dividing by just to make sure the negative 3 is being taken into account. So negative 2x times x is negative 2x squared. Again, matching up with the previous number. But negative 2x times negative 3 will give us a positive 6x. So we take that away to see what's left over. A positive 3, take away 6 will give us a negative 3x. The 9 will stay as it is. Then we repeat the process one more time. We have negative 3x. We're dividing it 3 by x. That will give us negative 3. We multiply the negative 3 by the numbers we're divided by to take into account the negative 3 in the divider. So negative 3 times x is negative 3x. And negative 3 times negative 3 is a positive 9. So we take these away from each other. We get 0. So it's 0. Therefore, x minus 3 is a factor. So we're seeing that you can have an educated guess on which numbers to look at. Sometimes, particularly squared numbers, then the square root might be one. Very often, -1 or +1 are factors. They're things you can look at. And you need to keep dividing until you find your first factor. Once you've found your first factor, then you can make some progress, because now we know that x minus 3 is a factor, but also the answer to the algebraic long division is a factor. The x squared minus 2x minus 3 is also a factor. So then you factorize the quadratic using easier methods. Now we know we need to get a 9 eventually, so it's a safe bet there's going to be another x minus 3 to get the 9. And it's going to be positive. We can only have 2 negatives in there for positive. We have 3 negatives, then it would be a negative. So the last one must be x plus 2. So I've used a bit of logic there to factorize it. I know I need 2 3's. We know that x plus 3 isn't a factor, so there must be 2 x minus 3's to get the 9, for example. If there's no logic like that you can use, then you can just factorize the quadratic using the methods you've used before. With simultaneous equations, it isn't a matter of getting all the letters on one side and all the numbers on the other, and then getting a value for the letter, because you're going to have more than one letter involved. So, for example, we might have something like 2x plus 6y is equal to 56. But we can't solve this using the methods we've used previously for equations because we have 2 letters. But because it's simultaneous equations, we'll be given a second equation with the same x and y values to help you solve it. So we're going to have x plus 5y is equal to 42. Now, our aim here is to eliminate one of the letters. Now, there's a few strategies for doing this, but the easiest one is to multiply one of the equations or both the equations until you have either the x or the y values matching up. Now, you need to spot how to do this. So have a look at the letters one by one. So, for example, if we look at the y's, we've got 6y and 5y. Now, there isn't a way, really, to get these equal to each other easily in multiplication. You'd have to multiply 6 by 5 and 5 by 6, so they're both equal to 30. If we look at the x's, we've got 2x and we've got 1x. Now, this is easier because we could multiply x by 2 to get 2x. And so that's what we're going to do. We're going to multiply all of the second equation by 2. And then this will give us a new question. We've got 2x plus 6y is equal to 56. And then multiplying by 2, x times 2 is 2x. 5 times 2 is 10y. And 42 times 2 is going to give us 84. So you're going to find some sort of way to make one of the variables line up. And now we have the x's line up. Once you've done that, you need to think about, can you add or subtract these to get rid of one of the numbers? And so with the 2's lining up, what we can do is we can do this as a column takeaway. And we can do 2x take away 2x is 0x. It's gone. That's why we did it. We can do 6y take away 10y is negative 4y. And we can do 56 take 84, which is negative 28. Now, both of these are negative. So a little trick here is we're going to solve an equation now to find what y is. So what we could do for our first step is that we could ignore the negative numbers. We could just say it's 4y equals to 28. And we're only allowed to do that if we do it to both sides. Effectively, the maths we've done to get rid of the negative sign on both sides is to divide by a -1 or multiply by -1. They'll do the same thing. Then we can divide both sides by 4 and we'll get y is equal to 7. So now we've got our first variable, y is 7. All we need to do now is take one of our 2 equations. Doesn't matter which one you choose. So the smallest one's normally easier. So let's take the x plus 5y equals 42. We know that y is 7, so actually x is going to be plus 35 because 5 lots of y is 5 lots of 7. So x plus 35 is 42. So what do we need to add on to 35 to get 42? We're going to have to add on another 7. So we can see that x is also equal to 7. At the end, you might just want to make your final answer really clear because the working out for them is both in different places. So you could write out the answers again, or alternatively, you could highlight them or something. Usually there'll be an answer line to write the full answer onto. So y is equal to 7 and x is equal to 7. Now, simultaneous equations can get more complicated. So let's look at some more complicated examples. So let's say we had 2x plus y squared is equal to 12. And again, because it's a simultaneous equation, we are going to need to have another equation to go through it. So we're going to have x plus y is equal to 6. Now, again, there's going to be a few different methods we can use here, but the gist of it is we've got two letters, an x and a y. We want to get rid of one of the letters. Now, we could do what we did with the previous question, and we could multiply the second part of it by 2 to get 2x and 2x and take them away from each other. And that'll be one method. Another method is that we could rearrange the second equation to be x equals something or y equals something. So we could say that x is equal to 6 take away y, just by rearranging it. And then once you've done that, you get your original equation, which is 2x plus y squared. But we know what x is. X is equal to 6 minus y. So we swap the x with what we've rearranged to get x equal to. And then we add the y squared onto that, and that's equal to 12. So let's expand the brackets. 2 times 6 is 12. 2 times negative y is negative 2y. Then we've got the y squared, and it's equal to 12. And now let's rearrange it to have the larger powers first. So we've got the y squared, taking away 2y. And then on the left-hand side, we've got 12. So normally we'd write plus 12. But on the right-hand side, it's equal to 12. Now, we could write it out like this. If we take 12 away from both sides, we'll get a quadratic. If we take 12 away from both sides, then it's going to be equal to 0. So now to find what y is, we need to factorize the quadratic. We have y in both because y times y will give us the y squared. We want two numbers that multiply together to give us, well, there's no number on the end, so it'll be 0, and add together to give us negative 2. So that's going to be a y plus 0 and a y minus 2. So then when we're writing down what y is, we're going to make the brackets equal to 0. So we could have y is equal to 0, or we could have that y is equal to a positive 2. And so that's how we get our first number. And then to find x, we can substitute into x plus y. So we want x plus y to be equal to 6. So if y is 0, x would have to be 6, so it equals 6. And if y was 2, then 4 plus 6 would be equal to 6. 4 plus 2 would be equal to 6. So x would have to be 4. And so that gives us two possible answers. We can have x is 6 and y is 0, or we could have x is 4 and y is 2. So when you get a squared number, you get a quadratic as part of the simultaneous equation, you might be getting more than one set of answers, so be careful with that. The last thing to look at is when we have 3 sets of variables and even 3 sets of equations. So we could have something like y minus x minus 2z is equal to 17. We could have x plus 2y plus 2z is equal to negative 35. And we could have 2y minus 2x minus z is equal to 13. Either the two methods we've used before. So the first method is called elimination, where you try and make two of the variables hold the same value and add them or take them away to kind of cancel them out. Or we can use the second method, which is by substitution, where we rearrange to make one letter as a subject and then substitute that in to get rid of it. If you want to use elimination, you're going to need to have two of the variables be the same. So for example, what you could do is you could multiply the top equation by 2, and that will give us y times 2 is 2y, negative x times 2 is negative 2x, negative 2z times 2 is negative 4z, and 17 times 2 is 34. And one of the other equations matches up with that. It's the bottom one, 2y take away 2x take away z is equal to 13. Now, what we want to do here is we want to do something to eliminate the variables. And if we take away, we get 2y take away 2y is 0y. Negative 2x take away a negative 2x. So it's a double negative, so it'll be that. Negative 2x plus 2x is 0. That's gone as well. And then negative 4z take away a negative z, double negative there, so that'll give us negative 3z. Then we can do 34, take away 13, which is 21. So we solve the equation. What we'd get here, if we divide both sides by negative 3, we get z is equal to negative 7. So that's one way, try and eliminate two variables at once, and you can find the value of the third one. I'm not going to do the rest of this. What you could then do is substitute z in. So every time you see a z, swap it with a negative 7. And then once you've done that, you can do another round of elimination, this time only eliminating one variable because we've already got rid of the z because we know what value it has. Alternatively, another method is that we could do a substitution method. So taking that top line again, we could change it into y is equal to 17. And then we can add x to both sides and add 2z to both sides. And then what we would do with this is then we would swap the y's in the second and third equations with 17 plus x plus 2z. And then that would give us, once we collected all the like terms, a regular simultaneous equation where you can then use, again, you might want to use elimination again this time, or you might want to do another substitution afterwards. So you have two options. So the top option being by substitution, and the bottom method being the elimination method. But no matter which method you choose, you then continue through and you find the values of x and y as well. And again, at the end, make sure the answers are really, really clear. So maybe write them out for a second time, maybe highlighting them, and just making sure that the answers are very, very clear. And for that last question, you might want to try it yourself. And what you should get is that z is negative 7, y would be negative 6, and x would be negative 9. With proof, the questions can be quite deceptive, as they seem like they're more complicated than they actually are. So let's say we are going to prove that 5 and then x plus 1 plus 5 and x minus 3 is equivalent to, so we've got a triple line, 10 with x minus 2. So how on earth could we prove this? Looks really complicated. So what you need to do when you have proof is just focus in on one part of this. And I'm going to focus in on the maths that's not been simplified. We're going to ignore that says proof. We're going to ignore that says equivalent to x minus 2 multiplied by 10. So if we just had the green highlighted section, what would we do? Well, we could expand the brackets. So multiply 3 by 5. So 5 times x and 5 times negative 1. And then multiply the second bracket. So 5 times x and 5 times negative 3. Now we've got an expression. We can simplify this. We've got two lots of 5x, that's 10x, and we've got a negative 5 and a negative 15. That'll be negative 20 altogether. So this is what we would do with just that expression. Once you've simplified it as far as you can, go back and have a look at the answer. So with the answer, we're looking at 10 outside of a bracket with x minus 2 inside of a bracket. At this point, you've got to think, like, what can I do to my simplified answer to get it in that format? And we've got a bracket, so are we going to factorize? So 10 and negative 20 have both got 10 as a factor, and we can divide by 10. 10x divided by 10 is x, and negative 20 divided by 10 is negative 2. And now we've actually got the expression that we need to be equivalent to. So to prove something, look at the unsimplified algebra, simplify it as much as you can. I want you as much as you can. Have a look at the answer and use that as a clue to think what your last step is going to be. One thing you can't do with proof, though, is use that final answer as part of your working out. Let's look at another example. So we're going to prove, and we've got x plus 6 all squared, take away x plus 4 all squared. And what we're proving about this, we're proving it's divisible by 4. Now, again, this looks more complicated than it actually is. So let's ignore the proof, let's ignore the divisible by 4. Let's just look at the expression we've been given, and let's see what we can do to simplify this. So firstly, we can expand the brackets. Now you might want to write the brackets out in full. So we have x plus 6 squared, it's been times by itself. And we're taking that away from x plus 4, and that's squared, so we're multiplying that by itself. So expand the brackets, x times x is x squared, x times 6 is 6x, 6x times x is 6x, and 6 times 6 is 36. Now we're taking away the same thing from the other bracket. So just expand the brackets first. So x times x is x squared, x times 4 is 4x, 4 times x is 4x, and 4 times 4 is 16. So we're just using your regular expanding bracket skills. Now, because we're taking this away, it's going to make everything in the second sequence of numbers negative. And if they're already negative, they'll become positive. So all these pluses are going to become minuses. We're effectively multiplying all the answers by -1. So be very, very careful with that. It's very common just to say that the x squared is negative, then have the rest be as it was and be positive. Now we can try and simplify. So we've got x squared take away x squared. So they're going to cancel out. Then we've got our x's. We've got 6x plus 6x is 12x. Take away 4x and take away another 4x. So altogether, that's going to give us 4x. Then we've got 36 and a -16. That's going to give us a 20. So we've simplified this as much as we can. And for something that looks fairly complicated, it has simplified down by quite a lot. And these questions will be designed to eliminate a lot of the terms as you simplify. So once we've done that, have a look at what the question actually says. And it says divisible by 4. It's telling us we can divide this by 4. How can we prove that we can divide something by 4? All we need to do is take 4 out as a factor. So look at 4x plus 20, and you can think, right, let's divide it by 4. If we can divide it by 4, then it's divisible by 4. If we can't, then it's not. So 4x divided by 4 is 1x, and 20 divided by 4 is 5. And since we were able to divide it by 4, the 4 outside the brackets proved that it's possible. Now we have our proof. We've shown by step working out that we can prove it. Now, one thing that's important here is you can't just skip to the last bit. So the first question, you can't just write 10, then x minus 2 in brackets. And for the last question, you can't just write 4 and x plus 5 in brackets. You need all the in-between steps as they form part of your proof. They show what you're doing step by step. If you don't have the working out here, then you're not going to get the max. And it's so important, let's make a note of it. So show working. Sometimes you need to do maths with graphs, but without looking at the actual graph. Now, one way of doing this is with midpoints. So let's say we want the midpoint of 6, 9 and 3, 8. So we're given 2 coordinates. Now, the way to find the midpoint is we're going to split this up into our x coordinates and our y coordinates. I'm going to look at these separately. Now, for the midpoint, all you need to do for the x coordinates is add them together, and to find the middle, divide by 2. So you basically find the average. So 6 plus 3 is 9, and divide by 2 is 4.5. The same thing with the y coordinates, 9 plus 8, which is 17. Divide it by 2, and 17 divided by 2 is 8.5. So then we can say what the midpoint is. The midpoint is going to be 4.5 and 8.5. And you might say something like m is equal to, and use m for midpoint. Another example, we're going to find the midpoint of, so let's have some negative numbers this time. So -7, 3, and 1, and -4. So again, we're going to have our x coordinates, we're going to have our y coordinates, and we're going to look at them separately. So x coordinates first, so -7 plus 1. Don't worry about which way around you add these together, you'll always get the same answer. -7 plus 1 is -6, and divide it by 2 will give us -3. Do the same thing with y. We would have 3 plus -4, so that would be 3 minus 4, and divide that by 2. So 3 taken 4 is -1, and -1 divided by 2 is -0.5. If we did that the other way around, we'd have -4 plus 3, which would be -1, and then we divide that by 2 to get -0.5. So again, if you're not really comfortable with the way adding this together, you might end up, 3 plus -4, and you might get confused by the plus and the negative together. Do it the other way around, it might make a little bit more sense to you. But you get the same answer either way, and that's that the midpoint is -3 and -0.5. As well as find the midpoints from 2 coordinates, another thing you can do is find the lengths between 2 coordinates. So, for example, we could find the length between, and we can have 9, 3 and 4, 3. Now, with this one, if you look at the y coordinates, we'll see that they're both equal. So there's no length in between the y coordinates. If we look at the x coordinates, we can see we've got 9 and we've got 4. So all we need to do is take the 9, take the 4 off it, and we get 5. And so that would be the answer. The length would be 5. Now, sometimes when you do this, you're going to get a length for both. So let's look at an example like that. So let's find the length between, and we're going to have 7, 6 and 3, 5. So when we have a look at the length between the x coordinates, we've got 7 and 3. So that would be 7 take away 3 is like the 4 in that direction. But then we look at the y coordinates, we've got 6 and 5. And so 6 take away 5 is going to give us a length of 1. So how do we reconcile the two lengths? Well, essentially what this is giving us is a triangle. Now we know that the x length is 4 and the y length is 1. And so we have a triangle like this. So if we want to find the length from one side of the triangle to the other side of the triangle, then we're going to have to use Pythagoras Theorem to find that. So that's going to be 4 squared, and that will give us the longest side squared. So then we would need to square root our answer. So they say you write Pythagoras Theorem all in one. So how are we going to answer it? So 4 squared is 16, 1 squared is 1, so 16 plus 1 will give us 17. And then we need the square root of 17. You could write square root of 17 as your answer if you want an exact answer, or you could have a rounded decimal, which will be something like 4.12 to 2 decimal places. So we've got an exact value if it asks for an exact value, and we've got a rounded value as well. The last thing we'll look at is a mix of these two things. So what if we wanted to find a quarter of the way from 6.3 to 2.1? Now this will give us an answer like a midpoint question. We're going to have a coordinate as our answer, not a length. However, with this, we're going to start off like we did with the length question. So we're going to find a distance between the two coordinates. So 6 take away 2, which is 4. I'm going to find a distance between the y coordinates. 3 take away 1 is 2. So then we take the coordinate we're finding something from. So not automatically the smallest to the largest, but we're from 6, 3. So a quarter of the way from 6.3 to 2.1, we're going to be going down, going closer to that. So we're going to be taking away from it a quarter of 4, our x difference, and a quarter of 2, which is our y difference. Now, sometimes we add it on. It was a quarter from 2.1. We'll be adding on to this. Sometimes it can even be a mix. So it depends if the coordinates going up or down. So you've got to be really careful with your negative numbers here. But for this case, the 6 is going to go down to a 2, so we're taking away our x coordinate. So a quarter of 4 is 1, so 6 take away 1 is 5. And our y coordinates are going down from 3 to 1, so we're also taking away the y coordinate. So a quarter of 2 is going to be a half. So 3 take away a half is going to be 2.5. A better way to write this is perhaps that we're going to add on a coordinate, but it's going to be a negative coordinate because the x coordinate's going down, and a negative y coordinate because the y coordinate's going down. And as I said, sometimes these will be positive, sometimes we mix of positive and negative. You've got to check what's happening on your journey. X journey is going from 6 to 2, it's going down, and the y journey is going down from 3 to 1. So that's why it's takeaways in just this case. One last thing to be careful of is that when we're saying that we're going to find a quarter of the way down the line, it might be written in other ways. Another way to write a fraction is to write it as a ratio. So it could be written as find the point in the middle of a 1 to 3 ratio. And a 1 to 3 ratio adds up to 4, which is where the denominator comes from in the fraction. And the first number is what we're looking at, which is the 1, which is the same in both. Pythagoras Theorem is a method to find the missing sides of triangles. Now, this has to be a particular kind of triangle, only works on right-angled triangles. Now, let's label the different sides of the triangle. A can be either one of the short sides. B would be the other short side. So A and B could be either way around, but C always has to be the longest side. And we've got a special name for that. We call it the hypotenuse. Now, what is Pythagoras Theorem all about? Well, let's have a look at side A. We can make a square out of side A. Now, side A is, let's call it 3 long. So we're going to have a 3 by 3 square. So let's call that in and label it. The next thing we're going to do is we're going to make a square on side B. Now, side B, as you can see, is longer. Let's call that a 4 by 4 square. Just got to follow the measurements of whatever that side is. And being a square, all 4 sides have to be the same length, otherwise it won't work. And the mathematics to work out the area of these squares is just to square the side of the triangle that you know. So you know the value for A. Again, let's call it 3. Then if you square it, you withdraw a square, by the way, then 3 times 3 is 9. So I have an area of 9. With the B square, the side length of B, let's say it's 4, then that'll be a 4 by 4 square, which will be 16 altogether. Well, okay, what does this mean? Well, let's have a look at the square for C. Now, the square for C is going to be even longer. So it's going to go all the way up here. And then we can join it up. Now, as we can see, this square is much, much larger. Now, what is the side length of C going to be? Well, let's say it's 5. Then this will be a 5 by 5 square. So we'll have an area of 25. So think about what we've done here. We've got an area 9 square, an area 16 square, and an area 25 square. So can we make any connections between those numbers? So what we're going to do is write those numbers next to each other and see if anything comes to mind. A 3 by 3 square, which is 9, a 4 by 4 square, which is 16, and a 5 by 5 square, which is 25. So we have 9, we have 16, and we have 25. So what's the connection? Well, you might have noticed that 9 plus 16 is equal to 25. And this is the essence of Pythagoras Theorem. If you take the a square, which is 9, and you add it on to the b square, which is 16, then you get the c square, which is 25. Now, how can we use this to find missing sides? Well, if you didn't know the side length of c, but you did know a and b, you can square a and b. You can work out what c squared is. Then all you need to do is find the square root of c squared to find c. Now, let's make a more general formula for this. So we are saying that c squared is equal to a squared plus b squared. So if you only wanted to find c and not c squared, you would have to square root both sides of the equation. So if you square root a squared, it's going to cancel out. That's why we did it. Then we have to square root the other side. Now we can't get rid of the square signs. We've got to put square root over the entire thing like this. And it's not going to cancel out the squared on both terms. It doesn't work that way. It's going to square root the answer to the two square numbers added together. So that's how we find a missing side C. That's the hypotenuse, the longest side. Now, what if we wanted to find a short side? What would we do? Well, we can rearrange the equation. So if we're saying that a squared plus b squared is equal to c squared, we can take a squared away from both sides. You can now rearrange an equation skills. It's a squared take away a squared, it cancels out, that's why we did it. But we have to take the a squared away from the other side. So now if we just wanted to find b on its own, again, we'd have to square root both sides, get rid of the square. And if we square root both sides, then we get this. We get the square root of the answer to c squared take away a squared. And that's going to be the exact same equation if you want to find a squared. You can just swap a and b around. A would be equal to the square root of c squared take away b squared. So essentially, if you're looking for the hypotenuse, the longest side, you're going to add the squares together. If you're looking for one of the two short sides, then you are going to take the squares that you have away from each other, with the first number being the square of c, which will be the largest number, so you don't get any negative numbers. Then you take away the small side that you do have. Now, the majority of the time, when you're using square roots, you're going to end up with a decimal answer. But there are a handful of triangles where all three sides are whole numbers that you can look out for. For example, 3 squared plus 4 squared is equal to 5 squared. 5 squared plus 12 squared is equal to 13 squared. 20 squared plus 21 squared is equal to 29 squared. 8 squared plus 15 squared is equal to 17 squared. And I think we'll do one more. 7 squared plus 24 squared is equal to 25 squared. Now, when I say there's a handful of these, that's not strictly accurate. There's a handful that involve small numbers. So what I've written here are all the ones that kind of happen before you get to 20. There will be more and more of these larger and larger and larger numbers. So there probably is, like, an infinite amount of these. There's one other thing that's allowed as well. You'll see multiples of these. So you might think about 3, 4, 5 is pretty simple, but then 20, 21, 29 is not very simple at all, is it? So I don't need to remember that. We don't need to remember these. But 3, 4, 5 is a good one to look out for. That's quite common. And multiples of it. So for example, if we double all of those numbers, then we're going to get 6 squared plus 8 squared is equal to 10 squared. And you can test that work. So 6 squared is 36, 8 squared is 64, and 36 plus 64 is 100, which is 10 squared. So again, you can also have multiples of these. So that's times 2. You can have a version that's times 3. So you can have 9 squared plus 12 squared is equal to 15 squared. And you can have multiples of the other ones as well. So for example, we take the 5, 12, 13, we can multiply that by 2, and we could have 10 squared plus 24 squared is going to be equal to 26 squared. If you're not sure about any of these, grab a calculator and test them out. The last thing to mention is that you can have questions where you have to use Pythagoras Theorem more than once. So let's take a pyramid. Let's say you want the height of a pyramid. That's from the center of the base, and it's going to go all the way up to the top until the apex of the pyramid. And it could be really hard to find the height because you don't have any measurements connected to it. But what you can do is that you could make a triangle that joins the slant like this, and this will be a right-angled triangle. So you're going to need the measurement of the slant, which you're probably going to be given, but then you also need the kind of radius from the kind of edge of the square base to the center. It's kind of like half the kind of diagonal measurement there. Now, how do we find that? Because we're not going to be given that, and we're not going to be given the height. Well, what you could do is you could use Pythagoras Theorem. Let's do this in another color. You can make a triangle with one side of the pyramid and another side of the pyramid like this. This will have a right angle if it's a square base, and you could find the length of that triangle, and you can see that half of that is going to be the half diagonal for the vertical triangle. So there are going to be some cases like this where in 3D you can use one triangle to find out a missing length on a second triangle that will get you the answer that you want. For example, the height of the pyramid, and we're doing it just by using one of the base lengths. If it's square based, then both sides will have a base. When we draw a line, we always want it in the form y is equal to mx plus c. And there's two important parts of this. M is the gradient, which is how steep the line is, and c is the y-intercept, which is where the line crosses the y-axis. If you line this format, it's fairly easy to draw it. Now, what's going to happen is you're going to be given lines that are not in this format, and you're going to have to handle it. So let's have a look at some lines like that. So the first line I'm going to look at is x plus 4y take 20 is equal to 0. And at first glance, it doesn't really look like it's a line equation, but you should be able to spot that it's got x and it's got y in it. Now, we want to make it the y equals. So we're going to take the y section of this, which is the 4y, and make that equals. Now, what do we need to get rid of? Well, we need to take the x away from that side, and we need to get the negative 20 away from that side. How do we get rid of an x? We take away x. How do we get rid of negative 20? We add on 20 to both sides. So we add on 20 to the left-hand side to make the negative 20 go away. It's going to reappear on the right-hand side as a positive 20. So now we've got it more towards our format. Now it's 4y and we want 1y. So how do we handle that? How do we make it into being a 1y? Well, to get rid of the 4, we have to divide by 4. So it's just the same as rearranging equations. It's the same as solving equations. So we divide by 4. We'd have negative x divided by 4. And then we'd have our 20 divided by 4. So to resolve this, you could leave it as negative x over 4. It might be easy to say, well, if you divide them by 4, another way to write it is negative a quarter x. Those two things mean the same thing. Well, the negative quarter makes more sense in the context of you're looking for a gradient before the x. And 20 divided by 4, we can do that. It's 5. So let's draw this line. We know the gradient is negative quarter. We know the y-intercept is at 5. So we find 5. And negative quarter means that, now with your gradient, this is the difference of y and x. So that's y divided by x. So that means that I'm going to move according to the y-axis is going to be 1, and the x-axis is going to be 4. And it's a negative gradient, so I'm going down. So I'm going to go down by 1 and across by 4. So again, my y movement is being down by 1 because it's negative 1. And my x movement has been 4 because it's over 4. And if we just repeat that movement every single time, and you can do it in the opposite direction as well, you can see we've got a nice straight line. Now, you go through this with a ruler. I'm going to sketch it, and it should look something like this. make sure it goes all the way to the end of the page and label it. So this was y equals negative a quarter x plus 5. We're going to have a look at one more example. We'll do this one in a different colour. 16x minus 4y minus 8 is equal to 0. Now, we want to get the y over to the other side so it's on its own. So we can add 4y to both sides, and that will give us 16x take away 8 is equal to 4y. Now, we used to see this as y equals, not equals y. And what we can do is just flip around the two sides. It doesn't matter which way around the two sides are. So let's write it the other way around. It's not going to do any harm, but it's going to be in the form we're used to. So 4y is equal to 16x minus 8. So now what we need to do is divide it through by 4 to get y on its own. So 4y divided by 4 is y, 16 divided by 4 is 4, and 8 divided by 4 is 2. So we've got y equals 4x minus 2. And again, we've got two things here. We've got our gradient, and we have got our y-intercept. The y-intercept is negative 2, so we find negative 2 in the graph. And the gradient is 4. Now, again, the gradient is a difference in y over x. And if it's a whole number, then we don't have an x value, or rather the x value is going to be 1. So this is going to be 4 over 1. So our y movement is going to be 4, and our x movement is going to be 1. And it's positive, so we're going upwards. So we'll go up by 4, across by 1, up by 4, across by 1. And we can do that in the opposite direction as well. And then again, I'm going to sketch the line. You'll do this with a ruler and a pencil, and it doesn't look straight. Rub it out and try it again. But I'm just sketching it just so you can see the process of drawing out a line. So I don't just show you a line that's appeared out of nowhere and you don't know how to draw it. Then we can label the line, and it's y equals 4x minus 2. Circle equations look like this. You're going to have an x, a bracket, and you're going to have a number with it, and it's going to be squared. And then you're going to have a y in a bracket with a number with it. That's going to be squared, and it's all going to be equal to a number. This is the format for a circle equation. Now, what do all these different bits and pieces mean? So the first important bit to look at is the plus 2 and the minus 3. Now, what the plus 2 and minus 3 represent are the centre of the circle. So this circle is going to have centre 2, negative 3. So we look on the diagram, that's going to be 2 to the right and 3 down. That's the centre of the circle. The next important thing to look at is the number at the end. That's a 64. Now, the 64 is related to the radius. So we can say that the radius squared is equal to 64. So the radius on its own is the square root of 64. And so the best way to write that's probably actually going to be to write that the radius is equal to root 64. And if you can work it out, the root of 64 is 8. That means that this circle is going to radius of 8 from the centre going upwards. It's going to be 8 spaces to the top of the circle. From the centre to the right, it's going to be 8 spaces to the right of the circle. From the centre to the left, it's going to be 8 spaces. And from the centre down, it's going to be 8 spaces, which actually just about goes off the graph. So let's draw the circle. So you have something like this. You're going to have to sketch it, potentially. If you sketch it, don't worry about it being too accurate. The best way to do this really is going to be with a compass. And what you can do is put the metal part of the compass on the centre of highlighted in green. Put the pencil part of the compass on one of the 4 pink dots that I've drawn. So you just do the radius in any direction that's convenient to you, and then draw a circle with your compass for an accurate diagram. So your circle is going to look like that. That's how you turn a circle equation into a circle. And sometimes you're given a circle, and you can look at the centre of the circle, you can measure the radius, and from that, you're going to be able to work backwards and create the equation of the circle. Now, it's not just equations of circles you have to find. There's also something called a tangent. Now, I'm going to draw a tangent on this circle, and a tangent touches the circle at one coordinate. And then it just goes off without touching any other part of the circle. Now, on this circle, this particular coordinate is going to be, should be 8, negative 8. So the tangent always has a point associated with it. Now, if we compare the tangent to the radius, let's draw a line from the radius to the tangent. What you'll find is the tangent should be at a right angle to the radius. Now, something you might be asked to do is find the equation of a tangent. So let's write down the question, or how to find a tangent. So we want to find a tangent of the circle x minus 5 squared plus y minus 4 squared equals 5, and it's going to be at the point 3, 5. Because you can have tangents at any point around the edge of the circle. Now, if you think about the centre of this circle, the centre of the circle is going to be at 5, 4. So I'm just looking at the numbers accompanying the x and the y. By the way, I didn't mention this, but if there's no numbers at all, then it's just going to be 0, 0 from the centre. Our tangent is going to be at 3, 5. So that's going to be something like, if I just sketch it out in the relative positions, it's going to be a little bit to the left and upwards from it. Now, what we're going to do here is we are going to find the equation of the radius, and the radius has length 5. Or rather, it's equal to 5, so it's going to be the square root of 5, actually, the length. And then once we find the equation of the radius, which we know 2 coordinates form, we can work it out, then we're going to take the negative reciprocal of its gradient to find the tangent. Because if you look at our first question, and the tangent I sketched on, it's at a right angle, and so that's a perpendicular line. Tangents are perpendicular. So it's perpendicular, you know it's going to cross at a right angle. So how are we going to find out the intercept and the gradient of the line? So the gradient is going to be the change in y over the change in x. Now with our line, in y's, we're going from 5 to 4, so that'll be -1. And from the x's, we're going from 3 to 5, which is a +2. So that's giving us a -1/2 gradient. Don't worry about which way around you do this, as long as it's consistent. So I started at the point on the tangent and went to the centre. We could do the centre of the point on the tangent. So you could do change in y from 4 to 5, which is +1. So let's write that down actually. But then the change in x in that same direction will be from 5 to 3, which will be -2. So that's just another version of writing -1/2. What you can't do is mix and match and go from x to go from the outside to the inside for one, and then from the inside to the outside for the other. You always have to start at the same point for both x and y parts of the coordinate. So now starting to form our equation, which is going to be y is equal to mx plus c. So y is going to be equal to a -1/2x plus c. Now we can take x and y coordinates. Now it doesn't matter which ones we use. We can use the centre or we can use the ones at the edge. I don't think either one of them is going to give us an easier journey really here, so I'm just going to choose the centre. So we know that y is going to be 4 for the centre, and we know that x is going to be 5 at the centre. And again, we can't mix and match here. They've both got to be from the same point. So that gives us 4 is equal to -1/2 times 5 plus c. That's 4 is equal to, so -1/2 times 5, 5 -1/2s. We could write it as 5 -1/2s. We could write it like this. Probably better to leave it like that actually. And then we can add on c. So on second thought, let's change this into a decimal. So 5 divided by 2 is 4.5. So what can we add on to -2.5 to get 4? So we'll have to add on 2.5 to go up to 0 and then another 4 afterwards. So we know now that c is going to be 6.5. So the equation of the radius, or this particular radius we're finding, is going to be y equals half x plus 6.5. And let's label what we're looking at here. So this is to find the radius. So now we want to find the tangent. So for the tangent, we're going to go through the same process. So I've just rewritten the radius working out to save a bit of space. Now let's find the tangent. So we know the equation for y equals mx plus c must be y equals, now it's going to be the negative reciprocal of a half. So we flip the fraction upside down. This gives us 2/1. And we make it negative. Now our gradient was already negative, so that's going to actually make it be a positive gradient. And 2 divided by 1 is 2. So negative reciprocal of -1/2 is 2. So it'll be y equals 2x plus c. And again, we can substitute into this. Now, it's got to be a point on the tangent, so it can't be the centre this time, so we'll have to substitute in the 3, 5. So we know that y is going to be the 5, and x is going to be the 3. So that gives us 5 is equal to 2 times 3 plus c. That's 5 is equal to 6 plus c. That means that c must be -1. So our equation is going to be y is equal to 2x minus 1. So the full process was sketch out the information you know about it and find the difference in y and x to find the gradient, with being the difference between 2 points on your radius line. That's usually the centre and the perpendicular point you've been given as a clue. Once you found the equation of the radius, and some substitution is required here, The equation of the tangent will have the negative reciprocal of the gradient, and again, you can substitute in to find your final equation. For the radius, you can substitute in either the centre or the perpendicular coordinate. They'll both give you the same answer, and they're both on the radius, that's fine. With a tangent, though, we have to write in that point on the perpendicular, otherwise it's not going to work. For area and perimeter, we have several diagrams and formulas to go through. To find the perimeter of an object, you need to find the sides, and normally be given the length of the sides, and the perimeter is all those sides added together. It's as simple as that. Now, this example is a triangle, but this could be any sort of shape. If it's quadrilateral, you'll have 4 sides to add together. If it's a pentagon, you'll have 5 sides to add together. We can also find the perimeter of curved shapes. For example, with the circle, the diameter is the measurement through the centre of the circle from one edge to another. It's going to go through the centre, and it's going to link up with both edges. And the formula for the perimeter of a circle, and a technical word for that is the circumference. The circumference of a circle is pi times d. So you get the pi button on your calculator, and then you would multiply it by the diameter. If it was a non-calculator question, then you wouldn't actually multiply by pi. You just leave pi on the end of your answer. You can also find the perimeter of more complicated shapes. For example, here we have a semicircle. Now, you might be given the full diameter, or you might be given a radius, and this is true for the circle as well, and with a radius, that's only halfway from the centre to the edge. So if you're given the radius, you want to multiply that by 2 to get the diameter. Now, for the perimeter of a semicircle, you do pi d to get the circumference of the full circle. And because it's only half a circle, you have to divide it by 2. Now, that isn't the full answer, because what that does, that finds the curved edge. But with things like semicircles, you also have the straight edge. And what's the length of the straight edge? Well, it's got a length of 1 diameter. So for a semicircle, you'd have to add on a diameter. There's other variations of this. If it was a quarter circle, then you would do pi d divided by 4 for the quarter circle, and then you'd have to add on 2 lots of the radius for a quarter circle, because then you'd have 2 straight edges. So it's just looking carefully at what you have and making sure you've added together all the curved edges and all the straight edges and done them in the correct proportions. Next, we will look at area. Now, with area, it's a really simple form that works for most things. The area is the base times the height. So we look at a rectangle. The base is a measurement at the bottom, and the height is a measurement at the side. Now, a really important thing about base and height is that they have to be at right angles to each other. Otherwise, they're not bases and heights. And the base is not necessarily at the bottom. The base could also be at the top, because these two sides are kind of parallel and the same length. And the same thing with the height. The height could also be on the other side. So you're not limited to the bottom for the base. Triangles also follow base times height. So we have the base of the triangle. This is the thing to identify first. Now, you don't have a straight base at the bottom. You can always rotate the triangle and kind of use one of the other sides. Key thing with a base, it has to be a right angle to the height. Now, the other two sides are not at right angles. So what is the height going to be? Well, you're just going to have to go straight up at a right angle from the bottom of the triangle to the top of the triangle. Must be at a right angle, and then that is going to be the height. So be very careful choosing the height with a triangle. So the area for this is also going to be base times height. However, there is a little difference. I'm going to show you the difference on the rectangle that we drew earlier. Now, if I cut this rectangle into like so, you can see that a rectangle is made out of 2 triangles. So when you do base times height, you actually get the size of 2 triangles. Now, we only have 1 triangle above. So what we need to do is divide the answer by 2. Because what base times height does is give you the size of a rectangle. So anything smaller than that, like a triangle, triangles are exactly half, you divide by 2. We can also find the area of circles, and the area of a circle is pi r squared. Now, what does that mean? Well, we covered already that the diameter is the line that goes all the way across the centre of the circle, from one side to the other through the centre. And we mentioned before as well, the radius is halfway. It's from one edge to the centre. So given the radius, that's great, use it. If you're given the diameter as some kind of trick, then you can divide the diameter by 2 to get the radius. Now, the last thing to go through are other types of quadrilaterals. So firstly, let's look at a parallelogram. Now, with a parallelogram, we do have a base. The 2 kind of diagonal sides are not at right angles. We can't use them as a height. So the height would have to be at a right angle to the base. Now, it turns out that with a parallelogram, the formula is still base times height, because although it's tilted, if you cut off the triangle at the start and you move it to the end, then you can adjust it to make a rectangle. So parallelograms follow the same base and height formula as a rectangle does. Kites look a bit trickier, but if you think of a base and a height, you could refer to a base and a height as kind of being the absolute maximum width the shape could possibly take and the absolute maximum possible height that a shape could take. So you could define bases and heights like this. Now, if we did that, we would get a full rectangle. We wouldn't get the kite. So how can we adjust base times height in this situation? Look at the shape. If we cut the shape up like so, we can see the shape is made out of triangles. And we have part of the triangle that's part of the area, and we have a triangle that's not part of the area of the shape. Now, if you do that for all four corners, what you're going to find is that the kite is only half of the total. So kites also follow the triangle formula, base times height divided by 2. So let's just draw some indicators on here and just show which shapes follow which formulas. Because the last one isn't going to be the circle form that's next to. It's going to be something a little bit different. The last shape is a trapezium. Now, again, we can find bases and heights with this. So we've got a base at the bottom, and at a right angle to it, we're going to have the height. Now, you might have noticed with the kite, for space reasons, I put the base at the top, not at the bottom, but they both be the same width because the top and the bottom are going to be parallel to each other and the same width. With this trapezium, if we drew the base at the top, you'll see that it's actually shorter than the base at the bottom. So we've got two bases with a trapezium. That means we're going to have a slightly different formula. And with a trapezium, what we're going to do is the area is going to be equal to, it's going to be base times height, but with the bases, we're going to add together the first base with the second base, and we're going to find the average of them. We're going to divide by 2 to find the average. And then once we've done that, then we times it by the height. So let's just label it on the diagram. We've got base 1 at the top, let's say, and base 2 at the bottom. You can also rotate trapeziums and have the same thing with a height. So you only have one base, but you've got 2 heights, then you find the average of the heights and then multiply by the base. For surface area and volume, we're going to have a range of diagrams with formulas. So the first thing we will look at is surface area. Now, surface area can happen with a variety of shapes. So we'll only go through one. And the concept is you're going to have a 3D shape. You want to find the area of a 3D shape. But 3D shapes are kind of all about volume, aren't they? And when you have a 2D shape, that's where you find area. So how can you get a 2D measurement on a 3D shape? Well, what you do is you just find the area of every single surface of the 3D object. So for example, here we have a triangular prism. So what you would do is that you would find the area of the triangle at the front. I'll do a little sketch. I'd label it. So this is number 1. And then you would work that out. And it's going to be a base times height divided by 2. Then you'd find the triangle at the back, triangle number 2. Now, if this is a prism, then they're both going to be the same, but they're not always going to be regular shapes. So it's up to you. You can either draw it out separately, which I'll sketch out here. And again, it's going to be base times height divided by 2. Or alternatively, you could find the value of the front triangle and then multiply by 2 to get the second one as well. It all depends on if they're the same size or not. So now we've found the front and the back. We've got the base defined. Now, with a perspective, it looks like it might be some kind of parallelogram, but it is going to be a rectangle. And even if it is a parallelogram, it's still going to be base times height. So I'm going to do a little sketch, label it 3, and that's going to be base times height. Then we've got the front face. Now, it's kind of hard to kind of label this with a perspective. Let's put a little 4 at the top here, actually, and draw an arrow to it. So this is the one that's facing us. Label it 4, and that's also going to be base times height. Now, depending on the prism, these rectangles could be the same size or they could be different sizes. Now, you know based on the triangles at the front. If these are equilateral triangles, then all 3 of the rectangles, because the back side as well, all 3 of the rectangles are going to be the same. So you can find one of them and multiply by 3. If it's an isosceles triangle at the front of the prism, then you find 2 of them and times by 2. Then add on the third one. Now, it's a scalene triangle at the front of the prism, then all 3 of these are going to be completely different. So the long version is what I've done here, and you would draw out every single surface and find the area with working out for every single surface. But there are shortcuts if some of these surfaces are actually the same size. So then what do you do for the answer? Well, the surface area is going to be shape 1 plus shape 2 plus shape 3 plus shape 4 plus shape 5. And depending on the object, there might be more or less of these. So for example, a cuboid is going to be made out of 6 rectangles. Triangular prism, like we see, is 2 triangles and 3 rectangles, and there can be all sorts of different variations to this. What they will do, though, is, and even if it's something more complicated like a pyramid, is that every single surface will be a shape that you know how to find. Typically, it's going to be rectangles and triangles, and you can also have circular ones, which we're going to move on to next. So, looking at a cone next, let's label all the parts of this cone. The first thing to think about is from the centre of the circle at the base to one of the edges. This is going to be the radius. Then we've got the height, which is from the apex of the cone all the way down to the center of the circle in the middle. That's the height. And then we've got the diagonal edge, and the length of that is called the slope. So for the surface area of a cone, we find the area of the base, which is a circle, so it's pi r squared. Then we add on to it the curved section. Now, these are the formulas that you need to kind of remember. You can't really derive these in the middle of your exam. So the curved section of the cone is going to be pi times the radius times the slope. And if you do that multiplication, add it onto the base. Don't forget to add it onto the circular base. That will give you the surface area of a cone. Now looking at a cylinder. Again, a cylinder is going to have a radius from the center to the edge. It's also going to have this side measurement between the 2 circles at either end of the cylinder. Now, you could call it all kinds of things. It's a height if it's stood up on its end. You could call it a width. I'm just going to call it a side. And so there's a similar process for the surface area of a cylinder. So the surface area, firstly, you have to find the area of the 2 flat circles. So there's 2 of them, and it's pi r squared for circles. Then we're going to add on to that the curved side. Again, this is something to remember. The curved side is going to be 2 pi h. If you multiply 2 by pi by the radius by the side. And again, that side could be a height. It could be a width, depending on how it's labelled. Next, we'll have a look at volume. And there's only 2 main formulas really to think about with volume. Now, the first one is the volume of a prism. Now, you might have learned different formulas, different kinds of prisms, but there's one formula for all prisms. And what we can do is we'll find the area of the cross-section. This is what I'm highlighting in pink. Now, the cross-section, this is the face of the shape that's the same all the way through. So you'll find at the back of this cuboid, there is going to be a square at the back, which is exactly the same in terms of the size of it. And actually, if I just highlight that a slightly lighter colour, you see that's the same size. So that's a cross section. Other thing that we need to know about is the kind of length of the shape. Now, again, it depends on the orientation of the shape. This could be a height, it could be a length or width, depending on what you want to use for it. I think what I'm going to do here is I'm just going to call it the side, like I did before for the cylinder. So this is the length that connects the front of the cross-section to the back of the cross-section. So for the volume of a prism, you take the cross-section and you multiply it by the side, and that's it. So this general formula works for everything. So for example, let's take the triangular prism that we use at the start for surface area. If you found the area of the triangle labelled 1, that would be the cross section. It would be the same size as the triangle labelled 2. So you'd find the area of triangle 1, then you multiply it by the length of the prism, and that's all you need to do. So the variation in different prisms is the cross-section being different. But once you've found the cross-section, you just multiply it by that side length. It even works for cylinders. So for a cylinder, all you have to do is do pi r squared to find the area of the circle at the front, which will be the cross-section, and then you multiply it by the side length. Now, cylinders are technically not really a prism in terms of definition, because kind of curved objects usually fall into different classification of shapes. So we normally reserve the word prism for these kind of shapes, like with triangles and squares at the front, rectangles, with straight lines, basically. But a cylinder does behave like a prism in terms of all the different formulas. So you can do that with a cylinder and treat it like a prism, find the area of the circle at the front, and then times it by the side length. Now, there's one more shape we can do this with, and it's a pyramid. Now, with a pyramid, again, it's going to go a similar way. We're going to have something like a cross-section. Now, with a cross-section of a pyramid, which I'm highlighting in pink, it's not a cross-section exactly because you don't have the same square at the top. What happens is that the kind of cross-sectional shape tapers off to a point at the apex of the pyramid. So it's not a cross-section. You could call it the base, perhaps. That'd be an accurate way to call it. The other thing that's important with a pyramid is the height of the pyramid. Now, it's going to be difficult to label that just because I've got base in the way. So I'm just going to label it at the side. The volume of a pyramid, you get the base and you multiply it by the height. And it's very similar to a prism. We find a kind of cross-sectional area and you multiply it by how long the shape is. We're doing the same thing here. We'll find the base and we'll multiply it by how long the shape is. But that would give us a cuboid. This isn't a cuboid, it's a pyramid. So our last trick is the volume of a pyramid is a third of the size of an equivalent prism. And just like with prisms, this will work with all sorts of pyramids. So if you had a tetrahedron, which we can call a triangle-based pyramid, then you would find the area of the base, which would be a triangle, so base times height divided by 2, and then you'd multiply it by the height of the pyramid, and then you would divide it by 3. And just like with cylinders, this works with cones. So with a cone, you would find the area of that base, which is pi r squared, the circular base. You'd multiply by the height, and then you would divide by 3. So again, just like with a cylinder not technically being a prism, a cone is not technically a pyramid, but it does behave the same way. So you can use the same formula. An important thing to note as well with pyramids is that for the volume, we're not using the length of the kind of slanted edge. We do use it for surface area if it's we use it for surface area if it's a pyramid or a cone. We don't use it for volume. So don't get confused between the slant and the height. They are different things. And the height should be at a right angle to the base. If it's not at a right angle, it's not the height. The last shape to look at is the sphere. Now the sphere is going to have a radius, and the radius is from the center of the sphere to the edge of the sphere. It's going to be the same no matter what direction you go in to calculate that. It'll be the same length. So we have two formulas for the sphere. The first formula is for the volume of a sphere. And the volume is 4/3 of pi r cubed. Then we have the formula for the surface area, and the surface area of a sphere is 4 pi r squared. Now, the last thing you should do here is look up the exam board of the exam you're taking and have a look at the formula booklet and just see which of these you'll be given in the formula booklet. And if you're not given some of these, then they'll be ones you have to remember. So you probably have to remember the volume of prisms and the surface area of prisms on your own, but some of the kind of curved shaped surface area and volume formulas you may be given. So have a look for that. With angle facts, we're going to look at all the different facts with angles in polygons. Then we'll look at angles in lines, parallel lines, and around points. The first set of angle facts to look at are what different kinds of polygons add up to. So the base fact for this is going to be that a triangle has got 3 angles, and these 3 angles add up to 180 degrees. And from that, we can derive the rest of the angle facts. So then when we have a look at a square, you might have forgotten what a square is. Same thing with rectangles, you might forget what they add up to as well. But what you can do is you can cut it in half from the corner, and you can cut it into 2 triangles. Now, we know that triangles add up to 180, so we've got 2 sets of 180. A quadrilateral, a square, a rectangle, other quadrilaterals, they're going to add up to 180 plus 180, which is 360 degrees for the interior angles. Same thing for a pentagon. Now, it's not very common to remember what the angles in a pentagon add up to. So what you do is you choose one corner, doesn't matter which corner you choose, and you join that corner up to every other corner in the pentagon. Like that. And you can see how many triangles it makes, and it makes 3 triangles. So we've got 3 lots of 180. So the interior angles of the pentagon add up to the total of those 3 180s, and that is going to be 540 degrees. Let's do one more example with a hexagon, but you can continue to, as many different shapes as you can, septagons, octagons, nonagons, decagons, even dodecagons. You just choose one corner, doesn't matter which corner you choose, and join that corner up to all the rest of the corners. So we're not just drawing triangles randomly, because you can draw as many triangles as you want in these. We are drawing the minimum number of triangles we can to make up the shape. And with a hexagon, we can see we've got a 180, we've got a second 180, a third 180, and a fourth 180. All of the interior angles in the hexagon add up to the sum of all those 180s, and it's 720 degrees. Now, you'll notice the number of triangles is 2 less than the number of sides in a shape. So let's say we had a dodecagon. A dodecagon has got 12 sides. So what you would do for the interior angles is you take 2 less than that, which is 10, multiply it by 180, and that will give you the total, which is 1800 degrees for the interior angles of a dodecagon. Now, what we found here is the total of the interior angles. So let's label that total of the interior. What you might also want to do is just find out how large 1 is. And to find out how large 1 is, you just need to divide by the number of angles. So a single interior angle for a triangle will be 180 divided by 3, which is 60 degrees. That'll only work though if it's a regular triangle. If it's a equilateral triangle, you can have triangles where they're all different. A single interior in a square, which is a regular quadrilateral, will be 90 degrees because it's 360 divided by 4. So with a pentagon, 540 divided by the 5 angles will give you 180. So a single interior angle is going to be 108 degrees. Then a single interior angle for a hexagon, you take the 720, divide by the 6 angles, and you get 120. And so, of course, you can do the same thing with a dodecagon. There's one more thing to talk about on this theme, which is exterior angles. Now, we take a triangle. What we're going to do is we're going to take a side and we're going to extend the side outwards. A new angle formed on the outside of the shape. Now, we can also take the next line, do the same thing, extend it outwards, and the third line, extending that outwards, and we get a pattern like this with these 3 new angles. And if it's a regular triangle, these are all going to be the same size. Now, what are these 3 going to be? Well, we know that the interior angle of a regular triangle is going to be 60 degrees. Now, we'll talk about this more in a moment, but angles on a straight line add to 180. So that means that the exterior angle must be 120 degrees, and that means that all 3 of them are 120 degrees. Now, what do the 3 of those add up to? Well, let's highlight it a different colour. So these are the exterior angles. So the total of the 3 angles in pink is 360. So what you'll find is if you do this pattern with all other shapes, they always add up to 360. And so this can be another way to find what the single interior angle is, because if all the exterior angles add to 360, you can divide by the number of sides of the shape. So for a triangle, that's divided by 3 to get 120. And then you can subtract that from 180, a straight line, to get what the inside angle is. For the hexagon, all the exterior angles go up to 360. Divided by 6 means that a single exterior angle will be 60 degrees. So take that away from 180 and you get the 120. That's a single interior angle. And so again, you can start to then calculate these things without diagrams when you're familiar with a formula for how these things work. So let's confirm that works with a square. So extend the lines outwards and label the new angle on the outside. Now we know that the interior angle is 90 degrees in a square. So take that away from 180 and the exterior angle will also be 90 degrees in a square. Now if we continue that pattern all the way around, creating these brand new angles, we can see that we're going to have 4. So the number of exterior angles is the same as the number of sides in the shape. They're all going to be the same if it's a regular quadrilateral, it's a square. So they're all going to be 90 degrees. And what do they all add up to? 360 degrees, just like with the triangle. So you can try out as many shapes as you want, but you'll always be getting 360. Now, I've been talking about the interior and exterior adding up to 180 because they're on a straight line. So where is that derived from? And actually, where are all these numbers coming from? Why is a triangle 180? So let's have a look at a circle. Now, a circle is defined as being 360 degrees. You can divide it by quite a lot of numbers. You can divide it by 1, 2, 3, 4, 5, 6. Now, 360 has got way more factors than this, so you don't stick a 0 most of those numbers. You can divide by those. So this is like the core thing where all the rest of the angle facts are derived from. Well, the first thing we'll look at is a semicircle. Now, with a semicircle, we call this angled on a line, which I just mentioned for the exterior angles. Now, you can see on a straight line, that's 180 degrees. Now, why are triangles 180? Well, if you take the 3 edges, the 3 corners, the 3 angles of a triangle, and you match them up with each other, they'll actually make a straight line like that. And so if you look at the new line I've drawn, you can see the 3 angles there. All 3 of those will make 180, and they will also make up a triangle. And once we define that a triangle is 180, then all the rest of the regular polygons can be made up of different kinds of triangles, and so we get the rest of them. The last thing to talk about are angles in parallel lines. So we've got a Z shape, like I've drawn out here, and the top of the Z and the bottom are parallel, go in the same direction, then the two angles on the kind of inside of the Z shape, they are going to be equal. Now, you can't say, oh, it's a Z shape. You've got to use the official term for this. These are alternate angles. Next, we have an F shape. Now, again, with the F shape, the two kind of lines coming off it have got to be parallel, otherwise this won't work. The angles inside the shape here and here are going to be equal as well. And we call these corresponding angles. So you can't say other than a Z shape, you've got to say the corresponding angles. And you may be asked why you're saying these angles are equal and these are the words you need to write. You might have a C shape. It might also be backwards or upside down or rotated 90 degrees and looking like an N or a U. So these can be rotated. And with a C shape, the angles on the inside like this. Now these aren't equal. These add to 180. So because of questions like this, it's tempting just to write, yeah, they're all equal. They're not. Sometimes they add to 180. And we call these co-interior angles. Now, there's one more. Above that, there is an X shape. And in the X shape, these aren't parallel because they cross over. You don't have to cross over a right angle or anything. They can be any kind of angles. And the angles that I'm highlighting here, they are also equal. And there's a name for that as well. These are opposite angles. So to recap, angles around a point add up to 360. Angles on a line are half of a circle, so that's 180. And angles in a triangle rearrange to be angles on a straight line, which is still 180. Once we know a triangle, we know a square is 360 because it's two triangles, and a pentagon is 540 because it's three triangles. With circle theorems, we have a series of angle facts that exist inside of circles. Now, the first circle theorem involves angles drawn from a chord inside of a circle. So let's highlight that chord. Now, what do we mean by angles drawn from the chord? So an angle drawn from the chord means that we draw a line from one end of the chord to the edge of the circle and a line from the other end of the chord to the edge of the circle. And in between those two lines, we have an angle. Now we're going to do the same thing again. We're going to draw a line from one end of the chord to the edge of the circle and a line from another end of the chord to the end of the circle, and they also create an angle. So what's the angle fact here? Well, let's call these angles X. So we have angle X, and then the other one would also be angle X. And what we're saying here is that angles drawn from a chord in this method are equal to each other. And the most important thing here is just recognizing what the chord is. And the exam questions, they don't always actually draw the chord on, so you have to recognize that it is actually there. The next circle theorem is a variation of this. So again, we're going to have a chord. Now, this chord is going to be special, so let's highlight it. This chord is going to go through the center of a circle, and therefore that makes it be a diameter. So a diameter is a special kind of chord that goes through the center. Now, again, we're going to draw an angle to the edge of the circle from both ends of the chord, or rather the diameter. Now, no matter where on the edge of the circle you place those two lines, what's going to happen is you're going to get a right angle. So let's do one more to illustrate that. So we're going to take lines from both ends of the diameter. We're going to meet at the edge of the circle, and you should be able to see that even though this isn't 100% accurately drawn, it's pretty close to a right angle. So angles drawn from a diameter 90 degrees. There's one more related circle theorem. So again, we're going to have a chord. I'm going to draw angles from a chord. Again, there's going to be a small difference this time. So we're going to draw an angle from the chord to the edge like we've done before. The difference this time is that the circle is going to have the center labeled on it, and as well as drawing an angle from the chord to the edge of the circle, we know that no matter where we draw that, it's going to be the same size. We are going to draw an angle from the chord to the center. And you can see that that angle looks quite a bit larger. Now, if we call the angle at the edge X, the angle in the center would be 2x. It's going to be twice as big. So angles drawn from a chord to the center are twice the size as angles drawn from a chord to the edge. Now, the next one is going to be a little bit different. So what I'm going to do is I'm going to choose 4 points on the edge of the circle. It doesn't matter where exactly these 4 points are. They could be anywhere. I'm going to call them A, B, C, and D. And I'm going to join them up. So I'm going to join A to B, B to C, C to D, and D back to A. And so we've got a quadrilateral, a 4-sided shape. And let's just highlight that, like we highlighted the chords and diameters. So there's something we can do with this. So with the angles, A and C are opposite each other. We can also say that B and D are opposite each other. And we can write a little equation. We can say that A plus C is 180 degrees. And we can also say that B plus D is 180 degrees. So those opposite angles are equal to each other. Now, there's a technical term for this, and we call it a cyclic quadrilateral because it's inside a circle. So say opposite angles in a cyclic quadrilateral add up to 180 degrees. For our next circle theorem, we are going to take a point on the outside of the circle. And what we're going to do with that point is we're going to make something called a tangent. Now, what a tangent does is it goes from a point on the outside of the circle, it hits the edge of the circle, and then it continues on. And it just touches the outside of a circle at one point. I'm going to do that to both sides of the circle, like so. And there's a few things we can say about this. So if I label the center of the circle, and then we label the tangents. So with the tangents, it's where the line just touches the circle at one point. Let's have a look at what happens when we join up the tangent to the center of the circle. So it doesn't look like much yet, but let's have a look at the angle that we have in between the tangent and the lines we've just drawn. And these angles are right angles. And let's label what we have. So we have a tangent, and let's highlight it. We've got another tangent, and let's highlight that. So the two new lines that we drew, let's highlight their new lines. They go from the edge of the circle to the center. Well, we have a word for that. It's a radius. So we can say that the angle between the radius and the tangent is 90 degrees. We can also say that the two tangents, they're going to be an equal length between the point that they start at and the edge of the circle. So it's not the entire tangent that's going to be equal, it's just a bit of the tangent that's highlighted in green. They're going to be the same lengths. And of course, as an extra detail, the two radiuses are also going to be the same length. Now, our last circle theorem is also going to involve a tangent. We're only going to look at one tangent this time. Now, what we're going to do is we're going to find the point on the circle where the tangent hits it, which is going to be here, and we are going to draw a triangle from that point. So we're just going to join that point on the tangent to two edges of the circle. It could be any two edges, doesn't matter where they are. And then once we've joined it up to two edges, we're going to join those two parts together as well to complete the triangle. Now we can say something about the angles in this triangle. So our first angle is going to be the angle here. Now you'll notice that angle touches the tangent and it touches one of the lines on the triangle. Now what we're interested in here is the angle that doesn't touch that line, the one over here. And those two angles are going to be equal. So again, I repeat, we're not looking at the angle right next to it. We're not looking at the angle that's on the same line as it. We're not looking at that angle. We're looking at the angle in the triangle that is nowhere near the angle we just looked at. Not next to it, it's not sharing the same line. Those two angles are equal. We can do the same thing at the other side. So we have an angle over here, and that angle is equal to the angle in the triangle that's not connected to it at all. They are equal. So we call the pink ones X and X, and we can call the purple ones, let's say, Y and Y. Now, how do we explain this? Well, it's quite complicated, so we have a word for it. We call this the alternate segment theorem. And so these are going to be the main circle theorems that you need to learn to solve problems. You'll also need a definition. So you can't just say, oh, these two angles are the same, or this one's a right angle, this one's double the other, just because I know. You will be asked in the exam, why this is. And by writing the reasons, you're going to pick up extra marks. You have to prove the thing that you're doing. Differentiation is a mathematical function. So the way it works is you take a function, f of x, and you're going to have something, for example, you might have a coefficient on the start of an x, and you might have a power. And the way that you differentiate, which will give you f dash x, is that you bring down the power to the coefficient. So you're going to multiply the a by the power. So the coefficient being multiplied by the power. And then with the x, the power, because we've kind of used the power to multiply it by the a, we reduce the power by 1. Let's have a look at a few different scenarios of this would actually look like in use. So let's say we have a function which is 2x to the power of 7. If we were to differentiate this, we would bring down the power. 2 times 7 is 14, and then reduce the power by 1. So then it would be a6. So going through that another time, we multiplied the coefficient and the power together. 2 times 7 is 14. And then we reduce the power by 1. Let's have a look at another example. So let's say we had a function And this function is going to be 2/3 x to the power of 3. So now we can start to introduce fractions. So when we differentiate this, we follow the same process, and we're going to bring down the power and multiply it by the fraction. So 2/3 multiplied by 3 would give us 6/3. And 6/3 is 6 divided by 3, which is 2. Then we have the x, and we reduce the power by 1. So let's go through that one more time. We multiply the fraction by 3, which will give us 6/3, and reduce the power by 1. And then we can simplify the fraction. 6/3 is 2. The final answer is 2x squared. Remember, when multiplying a fraction, if you want to find an equivalent fraction, which is the same size, you multiply the numerator and the denominator, which would give us 6/9, which is the same fraction as 2/3. If you want to actually make it 3 times bigger, you only multiply the numerator. Let's have a look at another example. So we have a function, and this function is 4x plus 8. So we're going to differentiate it. Now, the key to differentiating this is to think, well, what are the powers on the x? And there are no powers on the x, so we can add them in. On 4x, the power is 1, and on 8, the power is a 0. That's why there's no x there. So we bring down the power on the 4x, 4 times 1 is 4, and we reduce the power on the x because x to the power is 0. Now, as we can see in the question, if something's x to the power of 0, anything to the power of 0 is 1. So in the question, that's 8 times 1, which is 8. So here we've got 4 times 1, which is 4. So if you end up with a power 0, then you do not write an x in there. Here we have a power 1, as you saw, then we don't write the power, we do write the x. Now, what about the 8? Well, we do 8 times the power, 8 times 0, and that gives us 0. Then we reduce the power by 1 on the x, which gives x to the power -1. But the thing here is the coefficient is 0. We're multiplying it through by 0, so it doesn't matter what the x term is. If you multiply by a 0, you get 0. And so when we differentiate this, we end up with 4 as our answer. So what you can see here is, if you have an x to the power of 1, or just an x, it's going to reduce down into just a number. 4x has become 4. If you have something that's just a number, and you differentiate it, it disappears. It cancels itself out. And you can see here we had 2 different terms, and we differentiated them separately. So now we're going to look at an example with lots of terms. So we'll look at a function, which is 6x cubed minus 5x squared plus 7x minus 3. So when we differentiate this, we look at each term one at a time. 6x cubed. So we multiply the coefficient and the power. 6 times 3 is 18. And then we reduce the power by 1 down to a 2. Then we look at 5 times 2 is 10, and reduce the power down by 1. So a x to the power of 2 reduces down to x to the power of 1. But as we've seen previously, if it's power 1, we don't bother writing the power. We just write the x. Then we've got 7x to the power of 1. 7 times 1 is 7. Then we get x to the power of 0, which has a value of 1. You multiply by 1, it stays the same. The last one is -3. And as we saw in the previous example, normal numbers just end up cancelling out to be 0. Because we're multiplying it by the power, and there is no x there, so the power must be 0. And that gives 0. So we don't bother writing 0 down. So these are kind of the key set of differentiations that you're going to see. Now, there are some more complicated differentiations to look at. So the first kind of set of complicated differentiations are fractions. So you could have something like f of x equals 9 divided by x. Now, this isn't in the form that we've got the generalized form pink up at the top. It doesn't look like that. So our first step is to make it look like that. I need to know that if you're dividing by an x to the power of something, you can make it come up to the numerator, get rid of the denominator, but you've got to make the power be negative. So 9 over x is 9 over x to the power of 1. So we bring the x to the power of 1 up to the top, it becomes a -1. And now it's in the form we can use. So when we differentiate it, we follow our method. We're going to multiply 9 by the -1, which gives us -9. And we reduce the power by 1. And 1 below -1 is actually -2. So we get -9x to the power of -2. So make sure when you do the negative numbers, when you make them smaller, the actual digits get bigger as you get further away from 0. Now, there are a few examples like this where you have to kind of rearrange the equation to be in the form that you want. So we could have a function that's 2 over x to the power of 7. So we can rewrite that as 2x to the power of -7. So all we did is we got the denominator, we multiplied it onto the numerator, but if you do that, it's going to end up being a negative on top. When we differentiate this, we do 2 times -7, which is -14, and we reduce the power by 1. -7 becomes -8. Sometimes you might have one that's already negative, so you could have 6 over x to the power of -5, and we rewrite that as 6x to the power of 5. So if you bring in a negative power up to the top, it's rather than making the powers negative, kind of just reversing the sign. So positives become negatives and negatives become positive. Once we've done that, it's fairly easy to differentiate. 6 times 5 is 30, and then reduce the power from 5 to 4. The last one we're going to look at is a power. So we could have f of x could be the square root of 4x cubed. And when we rewrite this, and we can rewrite square roots as a power. Yeah, we need to square root 4 to get 2. When we square root the x cubed, we're going to get x to the power of 3 over 2. So just remember that fractional indices can be rewritten as roots and vice versa. So when we differentiate this, we'll bring down the power. 2 times 3 halves will give us 6 halves. And then the x, the power is going to go down by 1. So 3 halves will go down by 1. So that 3 halves is 1.5. So it goes down by 1. It's going to be 1 half. And then we can simplify the fraction at 6 over 2 is 3. So that gives us 3x to the power of a half. So really what we're doing here is we're using the laws of indices to rewrite our equation into the format that we're used to then properly differentiate it. The next complication is using trigonometry. So you might have a function, trigonometry in it. So we could have 8 sine x. When you differentiate sine, it becomes cos. Everything else stays the same. When we differentiate cos, so we have 8 cos x. Now, it's not an inverse operation, this. We don't go to then 8 sine. It's going to be a -8 sine x. So don't think that differentiating sin and cos are opposites of each other. They're not. The last thing to look at is a number called e. Now, when you differentiate e, so let's say a function is 2e to the power of x. When you differentiate it, we get 2e to the power of x. So e is quite an odd number. It's like pi, it's an irrational number. When you differentiate, it's got a very odd behavior, and essentially you can think that e is immune to being differentiated. Now, there is a situation where it being differentiated can make a change. So let's say we have f of x, and we have 8e to the power of 2x. Now, when you differentiate this, you're going to get 16e to the power of 2x. So while the power is not going to change, if the coefficient on the x in the power is present, in this case it's a 2, then we will multiply the coefficient on the e by 2. But again, the power is not going to change. So e is quite an odd number, and it has some very odd rules when you're differentiating it and integrating it. When looking at the second derivative, you'll notice that I've kept all the working out from differentiation. Differentiation is the first derivative. So what's the second derivative? Well, the second derivative is simply when you differentiate a second time. So show the derivative with 1 dash in our function. The second derivative has 2 dashes on your function. Now, all we do is just follow the exact same rules we followed for the first derivative. So we get the coefficient on the x, we get the power, and we multiply them together. So for our first question, 14 times 6 will give us 84. Then we reduce the power by 1. So x to the power of 6 becomes x to the power of 5. And there we have our second derivative. Moving on to the next question, second derivative. So we've got 2 dashes. We have 2x squared. So we multiply the 2 by the 2 to get 4. And then we reduce the power by 1. So the second derivative will be 4x. Second derivative, the next one. Now, the first derivative was 4. And we've said before that essentially this is 4x to the power of 0. So we do 4 times 0, which will give us 0. Then reduce the power on the x, which will be x to the power of -1. But because we're multiplying by that by 0, it's going to end up being 0 anyway, so that doesn't matter. So the second derivative of that is going to give us 0. So the second derivative, or even the first derivative of any number, will give you 0. Let's have a look at the next one. Now we've got multiple terms, and again, we'll just follow the same thing and do the derivative for each term. 18x squared, that will give us 36x. Negative 10x will give us negative 10. And the 7 is going to cancel out to 0, so we don't write it. So we just find the derivative of every single term like we did for the first derivative. And you'll notice that if you start off with a kind of polynomial like this, where you have an x cubed, an x squared, an x to the power of 1, and you've got a normal number at the end, practically an x to the power of 0. So you've got one of each. What's happened is we've got 4 terms in our original question, we've got 3 terms in our first derivative, and 2 terms in our second derivative. Each time we differentiate, we lose our whole number term, so the total number of terms goes down by 1. Now, with the next set, all of these have, well, some of them have got negative numbers, so be very careful with those. So the second derivative of our next question, we've got a -9 for a coefficient and -2 for the power. So -9 times -2 gives a +18. Then we reduce the power on the x, so it's going to go to -3. So you can see we start with -1 in the original question, -2 for the first derivative, and -3 for the second derivative, reducing by 1 each time. We've also got a double negative for the next one. Coefficient is -14, and our power is -8. So 14 times 8 is going to give us 112. Then reduce the power by 1 to -9. Now, for our next one, we didn't have any negative numbers. This will be a little bit easier. So we've got 3 times 4 is 12, and the 0, so 320, and reduce the power by 1, 120x cubed. This stays consistent as well when you have functions that have a fraction as your power. So we're going to do 3 times a half, which will be 1.5, and then reduce the power by 1. A half, take away 1, will give you a -half. So I can show you how fractions can make this tricky, but just be patient and follow the rules, you should be okay. 3 times a half is 1.5, 1.5, and then a half take away 1 is -1/2. Moving on to trigonometry. So what the second derivative is 8 cos x. Now that's actually the question afterwards, wasn't it, that we did before? So the answer is going to be -8 sine x. Differentiating cos into sine will give you a negative number. Differentiating sine into cos, we just swap the sine with cos. And then second derivative of an e, well, if the first derivative doesn't change it, the second derivative isn't going to change it either. Then looking at the last one, we've got 16e to the 2x. That'll end up being 32e to the 2x. So if you differentiate e multiple times and it's just power to x, you're going to have no changes. But if you differentiate e and it does have a coefficient on the x and the power, then you will be bringing down the coefficient, but the coefficient and the power itself won't be changing. The gradients of tangents and normals are one way to kind of make sense of why we learn differentiation. So let's take a line. So we've got y is equal to 5x squared minus 6x plus 9. And we're going to be asked something about this. So we might be asked to find the gradient at 217. So let's do a little sketch of the graph to kind of visualize what's going on here. So we're going to have a 5x squared minus 6x plus 9 graph, and we're going to have a point on that curve. Let's label the graph, and let's just label the point. I'm labeling it somewhere random just to illustrate what we're doing here. So what do we mean by the gradient at this point? So what we want is, at that particular point in the curve, how steep is this line? And the gradient is basically going to form a tangent to the curve like this. And this tangent is going to have the same gradient as the curve at the point it hits the curve. So how do we find the gradient? So we take 5x squared minus 6x plus 9, and we differentiate it. Now, we're going to use some different notation here. So if it's y equals, our differentiation notation will be dy by dx. We differentiate, so we'll bring down the powers. 5 times 2 is 10, reduce the power. 6 times 1 is 6, reduce the power. And we've got 10x minus 6. So that's the equation of the gradient of the curve. So that's what differentiation does. It gives you the gradient. Now, we wanted the gradient at a specific point. We wanted it at 217. So we want to take our 10x minus 6. We want to replace the x with the 2 and then take away 6. So 10 times 2 is 20, and take away 6 is 14. So the gradient at 217 is 14. You differentiate the curve, and once you've differentiated the curve, you have an equation representing the gradients, and you just substitute in the x coordinate. So now let's have a look at another curve. So let's look at y is equal to x squared plus 3x plus 9. And we're going to want for this, I want the tangent and the normal equations at a coordinate, and that's going to be -4, 13. So how do we do this? So again, it might be useful to visualize the curve, x squared plus 3x plus 9, and visualize the point on it. So the tangent is going to be a line that just touches the curve at that point. And the tangent is going to be the same equation or rather the same gradient as the curve at that point. The normal is the line that passes through this at a right angle. And these are the two lines we're going to find the equations of. So the first job is to differentiate our equation. So dy by dx, we've got x squared, that'll become 2x. We've got 3x, that'll become 3. And 9 will become 0. So we've differentiated. Now, when we want the gradient of the curve and the tangent, what we want to do is substitute in the x for a -4, because that's the point. So we'd have 2 times -4 plus 3. And this is going to give us 2 times -4 is -8, and plus 5 is -5. So then for the tangent, we can say its equation is y equals -5x plus a constant. For the normal, we can say the equation is y equals a fifth x plus a constant. And so what we've done for the gradient of the tangent is just have that same number, -5. But for the normal, we've taken the negative reciprocal. And the negative reciprocal means that you flip the fraction upside down and you reverse the sign. Reverse the sign of the negative gives us the positive. That's why it's a positive fifth. And flipping the fraction upside down, well, -5th could be written as 5/1. So if you flip it upside down, you get 1/5. Now we want the values of the plus c's. So then we also substitute in the y coordinates. So for the tangent, we're going to have 13, substituting y, is equal to -5 times -4 plus c. And we can rearrange to find what c is. -5 times -4 will give us 20. So we need to take 7 away from 20 to get 13. The c for this must be 7. So let's replace that in our answer. Do the same thing for the normal. The normal is going to be equal to 13, so we're shooting in the y. But this gradient is a fifth multiplied by the -4, and we're adding on c. So if we rearrange this, now a fifth times -4 is -4/5. So to get from -4/5 all the way up to 13, we need to add on 4/5 to get to 0, and then another 13. So it's going to be 13 and 4/5. And again, we're going to go back to our answer and we're going to replace that. So the gradient of the curve at that point is -5. The equation of the tangent is y equals -5x plus 7. And the equation of the normal to the tangent and to the curve is y equals a fifth x plus 13 and 4/5. But this is all true only at the point -4, 13. If you took a different point on the curve, then you would have a different gradient, a different tangent, and a different normal. Now we've got a lot of working out here. Let's just highlight our answers. The answer to the first question was 14, and then to the second question, we had the tangent equation, so it's a two-part question. Minima and maxima are another practical use of differentiation. So let's say we have a line, y equals x squared minus 6x minus 4. And let's just do a little sketch of that line. Now, what we have on this line is something called the minimum point. Another word for that is minima. And we can use differentiation to find out where that point is on the line. So firstly, differentiate your equation. So x squared will become 2x, and -6x becomes -6. So as usual, multiplying the power by the coefficient on the x, and then reducing the power by 1. So now we've got an expression for the gradient of the curve at all different points. Now, what does this have to do with the minimum point? Well, the minimum point and the maximum point as well is the turning point of the curve. And that means that the gradient is equal to 0. And if we drew a tangent to this, the tangent would be a completely flat line with a gradient of 0. So we know the gradient has to be 0 at the minimum, and we've differentiated our line to get an equation for the gradient. So all we need to do is put the two things together. And we have now, for the gradient, 2x minus 6 has to equal 0. So now we solve the equation. 2x is equal to 6, so x is equal to 3. So we know that the minimum point is at an x coordinate of 3. Now, it's not enough to just know the minimum point and the x coordinate of it. We also want the y coordinate. And we've got an expression for the y coordinate. It's our original question. Y is going to be equal to x squared, take away 6 lots of x, take away 4. So just substitute that x into our original equation. So 3 squared is 9, take away 3 times 6, which is 18, and take away 4. So 9, take away 18, take away 4 gives us negative 13. So we know the minimum point of our curve is at 3 and negative 13. We got the x is 3 from differentiating the curve and making the expression for the gradient equal 0 and solving. We got the y from substituting that x value into our original equation. Now we're going to look at a more complicated line. So we're going to look at y is equal to 2x cubed minus 5x squared minus 4x plus 1. And what I'm going to do for this is I'm going to find the first derivative, which will be 6x minus 10x minus 4. And I'm also going to find the second derivative, which we call d2y by dx squared. So then differentiating that, 6x becomes 6x squared, becomes 12x, and negative 10x becomes negative 10, and the 4 becomes 0. So I was preemptively differentiated twice because I'm going to need these for the working out we're going to do in a moment. Now, cubics can get quite complicated, but with a cubic, it's going to be something like this. And there's going to be 2 important points here, or rather 3 important points. There's going to be a minimum point. There's going to be a maximum point. I'll just redraw this slightly to make it more clear. And with a minima and maxima, these are called local minima and maxima, because I'm saying that this pink point here is the minimum point. But if you look over to the side, we can see that actually the graph does dip further down. So it's not the minimum point for the entire graph, but it's a local minimum point for the squiggly part of the cubic. And the same for the maxima. You can see that's not actually the highest the graph goes. It goes higher on the left-hand side. We just call it a local maxima. There's another important point here, and this is the point of inflection. Now, the inflection point is kind of the turning point where the graph kind of switches between being part of the minima curve and part of the maxima curve. Now we're going to look at the maxima and minima first, and it's similar to what we did with the quadratic in the first example. So we take the expression for the first derivative, which is an expression for the gradient. That's 6x squared minus 10x minus 4. And we want this to be equal to 0 at the minimum and maximum point, because the gradient at both points is going to be 0. Now we can see there's 2 of them. In the quadratic, there's only 1, but here there's 2. But it's a quadratic, so you can get 2 answers out of a quadratic. So we can factorize the quadratic, or you could use the quadratic formula, depending on what kind of answers you get. But if we factorize this, we get something like 3x plus 1 and 2x minus 4. And you can factorize this using any method you like, but this is one factorization. This gives us that x would have to be equal to a negative third to make the first bracket be 0, and x would need to be equal to 2 to make the second bracket be 0. So we've got 2 answers for x. All we have to do at that point is substitute both values of x into our original equation. So it's substituting x is equal to negative third into the equation, and x is equal to 2 into the equation. And that would give us the y values. Now, we went through substitution in the previous example, so I won't do that again. You should know how to substitute. The values you should get, y is equal to 1 7/10, and y is equal to negative 11. I'll draw a little arrow over to the method you need to be using where you do the substitution. So now we've got the coordinates for the minima and maxima points, but which one's which? Because I've just kind of drawn that diagram at random. It could be rotated the other way around, for example. The maxima could be first, then the minima. So how do we know which one's which? Well, as well as substituting our values for x into the original equation to get the values for y, we are also going to substitute the values for x into the second derivative. And the second derivative is going to give us a bit of an idea of if these are maxima or minima. The second derivative gives the rate of change of the gradient. Now have a look what happens after a minima. After a minima, the gradient's going upwards, it's positive. And after a maxima, the gradient's going downwards, it's negative. So if we substitute the x equals negative a third into the second derivative, you get 12 negative thirds take away 10. That's going to be a negative number. And if it's a negative number, it's going to be a maxima. I'm going to write negative, therefore maxima. With the other one, when x is equal to 2, there'll be 12 lots of 2 take away 10. So that'll be 24 take away 10. That'll be positive. So if it's positive, we can see in the diagram that after a minima, we have a positive gradient. So it's positive, therefore, it's going to be a minima. And we could do this with the quadratic as well. So with the quadratic, when x is equal to 3, the second derivative, 2x minus 6, the second derivative is going to be a 2. So that's positive. And so that tells us that this is going to be a minima, which is the way I drew it. So now we know which one's a maximum and which one's the minimum. The last thing to look at is the point of inflection. Now, for the point of inflection, what you need to do is get the second derivative, the rate of change of the gradient, and we need to look at when it's 0. Because if we have a look at our diagram again, the point of inflection is in between the minima and the maxima. Now, if let's have a look at the gradient. So the gradient is getting bigger and bigger and bigger as it gets to the point of inflection from the minima. After the point of inflection, the gradient starts to slow down and get smaller and smaller and smaller. So equals 0 will be that middle point. If we solve, we'll have 12x equals 10. X is equal to 10 divided by 12, which is 5/6. And then again, what you would do is you would take the x is 5/6 and you would substitute it into the original equation to find out where y would be. Now, it's quite a complicated substitution because you have to, do 5/6 cubed and times it by 2 and so on. But you should get something like y being equal to negative 4.65 to 2 decimal places. So the two things to take away from this is that the first derivative, dy by dx, is the gradient. And there are special places on some graphs where the gradient is 0, the minimum and maximum points. d2y by dx squared, our second derivative, is the gradient's rate of change. You can see the gradient is a rate of change of the line, and the second derivative is a rate of change of the gradient. And there's special points on lines where that's equal to 0, and that's a point of inflection on cubics and above. Notice that quadratics, you can't substitute into it for a quadratic. The second derivative for our first example is just a 2. There's no x in there, and so it's always the same number. So that means that it's always going to be a minimum, and there is no point of inflection for a quadratic. But there are for cubics and ones with high powers. Integration is the inverse operation to differentiation, and so we can have a similar general rule. Now we have this kind of curvy S symbol, and this is what we use to show that we're integrating. So let's say we have a coefficient on an x, and we have a power. Then at the end, we have another bit of notation, the dx. Now the relevant part of this is just the middle part. This is the bit that we're interested in. The rest is, technical notation. It just tells you what kind of maths you're doing. So we're only looking at the pink highlighted area. So what do we do with this? Well, with differentiation, you multiply the coefficient and the power and increase the power. So here we do the opposite. We are going to divide our coefficient by the power, and then we're going to increase the power. Now, when I say we divide by the power, we actually divide by the new power. So the power is b, we divide by b plus 1, and our new power is b plus 1. So let's look at some examples. So let's say that we are differentiating 5x to the power 6. Again, we're only going to focus on the maths in the middle. The curly S symbol, the integral symbol, and the dx, just part of the notation that shows the kind of maths we're doing. So we're going to take the 5 and we'll divide it by the new power. Now, what's the new power? Well, it's power 6. We're increasing the power to a 7. So we divide by the new power, which is a 7. So we get 5/7 x to the power of 7. We've increased the power, and we divide the coefficient by the new power. Just like with differentiation, you can do this with multiple terms. So we could have 7x plus 8. So again, we focus on the middle part, and we just integrate both terms. So with the 7x, the power on the x is a power 1. If there's no power, it's power 1. So we need to increase that to a power 2. That means a 7 is going to be divided by a 2. Then we look at the 8. Now, with the 8, if there is no x, that's practically x to the power of 0. So if we increase the power, we get to the power of 1. So we're adding 8x to the 1. Now, there's one extra thing here you might notice, which is that when you differentiate, you lose a term. So let's say if we differentiated 7x plus 8, we would reduce the power to get 7x to the power of 0. And then with the plus 8, that's 8x to the 0. We'd multiply the coefficient by the power and get 0x to negative 1. And so you multiply something by 0, you get 0. So we don't write the 0x to the negative 1. We lose a term. And then the 7x to the power of 0, we just write 7, because x to the power of 0 is 1. So we lose terms. And in integration, we gain terms, but we've no way of knowing what that number was that we've gotten rid of. There's no way to work backwards to it. So what we do in integration as well is we write plus c on our answer, plus a constant. And that says we could be adding on to this a whole number. But given the information we've got, there's no way to kind of work backwards and work out what that number was. Let's look at another example. So let's say we differentiate 9x to the power of a half. So we've got a fractional power here. And as usual, we focus just on the numbers in the middle. So what do we do here? So again, we take the x and we increase the power. So a power half plus 1 will give us a power of 1.5. Or you could write 3/2. Now we need to divide 9 by 1.5. So how many 1.5s go into 9? Well, actually, this is something you can do. You can actually count up how many 1.5s go into 9. So you say, well, 1.5, 3, 4.5, 6, 7.5, and 9. That was 6 that went in. So we say we've got 6x to the power of 1.5. Alternatively, it might be easier to write. You could just write 3/2 for this instead. Takes up a little less space. Now, just like with differentiation, we can write out questions that initially don't seem like we can do them. So we could have 2 over x to the power of 5. And just like differentiation, what we need to do here is change this into something in the format we're expecting. A coefficient, an x, and then a power. So we can write 2 over x to the power of 5 as 2 times x to the power of -5, just using our laws of indices. And now we have something we can handle. We take the x, when it increase the power, and a -5 increase, not -6, it's -4. If you increase the power, it's going closer to 0. That means that the 2 will be divided by -4. That gives us -2/4. Now 2/4 is a half if you simplify it. So we'll have a -half x to the power of -4. There are other situations where you would have to rearrange this. So, for example, one situation would be having roots. So let's say we had the cube root of x squared. So again, we're focusing on that middle section. We've got to rewrite it into the form we need to actually integrate it. So that's the same as x to the power of 2/3. So any roots are just the denominator on your power. So then we're going to increase the power. Now 2/3, if we increase it by 1, that'll be 1 2/3. You write that as a fraction. We could write it as 5/3. And then we've got no coefficient at the start. Now if you don't have a coefficient at the start, it's 1x to the power of 2/3. So then we're dividing 1 by our power, which is 5/3. Now if you divide a fraction by another fraction like this, and you've got 1 over a fraction, you're attempting to find the reciprocal of it. So that's going to be 3/5. So that'll give us 3/5 x to the power of 5/3. And what I've done is I forgot to put the plus c's on my last 3 answers. And this is really easy to forget. So always remember to put those on. That's just saying again that there's another bit to this that maybe we don't have. There's no way of working backwards with integration to get this number. Now, we also have some special cases. So we have trigonometry, for example. So if you are differentiating sine of x, then we differentiate it, you get a negative cos. And of course, it's plus c. If you're differentiating cos of x, then you get sine x. So notice they're not inverses of each other because you integrate sine, you get a negative version. With integrate cos, you don't get a negative version. There's also a version of this for tan. Now we call this sec squared. And if you see that, it's just a kind of version of tan. And it will integrate to give you tan. Another thing to think about with this is we can have kind of coefficients come to the front like in the other examples. So let's say we are differentiating and we've got 3 sine 2x dx. Now, the number on the x actually comes out like the powers do in the other examples. So this will give us 3/2 sine goes to cos, and it'll be a negative cos. And then the number in the bracket is going to stay the same. So it'll still be 2x. And then that also will be plus c. E works in a similar way to differentiation, where if you're integrating e to the x, your answer is just e to the x. If you integrate in something like 4e to the power of 4x, then what would happen is that 4 would come down and divide your coefficient at the start and give you 4 divided by 4, e to the 4x. And so then that would just give you e to the 4x. And with both of these, as usual, we have the plus c, even at c. So here are most of the cases of integration that you should encounter. Definite integrals are a practical use of integration. So let's say we've got a line, y equals 8x minus 3. So let's just do a little sketch of this. It's not going to be very accurate. So it's going to be quite a steep gradient, and it's going to be going through -3. So something like this. Now, what we're going to do here is we're going to find a question involving integration. Now, it's going to look like this. We're going to have the integral symbol and 2 numbers next to it. We're going to have 4 and 3. We're going to have the 8x minus 3 and the rest of the integration notation. So you can see we've got the kind of the y equals part here. So we've got the equation of our line. Now, what do the 4 and the 3 mean? So the 4 and the 3 mean that we're going to find the area in between 4 and 3 on the x-axis. So we're going to be finding this part of the graph here. Because when you integrate, what it does is it finds the area underneath the graph. And so we need to find that area. So how does integration help? Well, the first thing to do is actually to integrate. We're going to take the x, we're going to increase the power and divide the coefficient of that x by the new power. Then we go on to the next term. Now, again, with that, we're going to take the x. There isn't one, so there isn't an x. We're going to pop one in. Because that -3, that's -3 to the x to the power 0. So now it'll be x to the power 1. And we divide the 3 by the new power, which is 1. 3 divided by 1 is 3. And now it's integrated. So how do we find the area under the curve using this? Well, we substitute in the 4 and the 3. And you might see some square bracket notation for this. So when we integrate with 8 over 2, which is 4, so we've got 4 lots of 4 squared, take away 3 lots of 4. And remember, I forgot to write it in again, it's plus c when you integrate. So we've got to put in that plus c. There might be something else there. Once we find the answer for 4, we take away from it the answer for 3. So now we substitute in 3. So we've got 4x squared, so that'll be 4 times 3 squared. Then we've got the -3x, that'll be 3 times 3. And then we've got the plus c. And so what we need to do now is do the substitution and get some answers out of this. So working through this, 4 squared is 16. Multiply it by 4, you get 64. We're taking away from that 3 times 4. And we're adding on c. 64 take away 12 is going to give us 52. So we have 52 plus c from our first bracket. The second bracket, we're going to have 3 squared is 9. Multiplied by 4 gives us 36. Then we're taking away 3 times 3, which is 9. And we're adding on the c. Now, a really critical thing here is we are taking away the second bracket. So we've got 36 take away 9 is 27. But on our final answer line, we're not going to be adding on 27. We're taking away the 27. And then we're not adding c. We're going to be taking away c. So remember, all the answers from the second bracket have to become negative. Or they're already negative, they need to become positive. Now, let's have a look at this answer line. So we've got 52 take away 27. Which is 25. And then we've got the plus c and a takeaway c. So those c's have cancelled out, they've gone away, so we don't need to worry about them. And so now with this answer, 25, we know that the area under the curve in our little diagram here was 25. So definite integrals can find the areas under curves. Let's have a look at one more example. And look at a slightly more complicated example. So we're going to have y equals 5x squared plus 2x plus 9. And so when we integrate this, we want to get the area between 0 and -3. So let's write the integration notation. And we can see the equation of our line in the middle of that. So the first thing to do is going to be to actually integrate. So with the x squared, that will become x cubed, meaning that the coefficient 5 will be divided by 3. Then the next x will become x squared. So the coefficient 2 will be divided by the 2. Then move on to the next term, the 9, so that'll go up to 9x. And we'll have the plus c at the end. So now we're going to write out our square brackets. And when we do our square brackets, we're going to think about the first bracket. We are going to be substituting in 0. So our first 3 terms all have x. And if x becomes 0, Now we're multiplying by 0, so those terms just going to become 0. So the only thing we'll have left in the first bracket is the c, which doesn't have an x connected to it, so it won't be multiplied by a 0. So if you've got a 0 involved, that bracket's going to be 0, and we only need to look at the second bracket. Now that second bracket is going to have our 5/3 x cubed, and so we'll substitute in -3 and cube that. Over our next one, with the x squared, 2 over 2 is 1, so it'll be 1x squared, so that'll be -3 squared. Then we're adding on the 9x, which would be 9 lots of -3, and then we've got the plus c at the end. So working through this step by step, so -3 to the power of 3 will give us -27, and we're going to multiply that by 5/3. So multiply by 5 and divide through by 3. That will give us -45. Then we have -3 squared, which is going to be 9. Then we have 9 times -3, which would be -27. And we'll have the plus c. So when we get to our final answer line, we've got the positive values from the larger bracket, which was 0, so we have a c in there. And the second bracket we're taking away, all of these are going to become negative. If they're not already negative, then they'll become positive. So we have the -45, we added 9, and we took away 27. And altogether, that's -63. We'd have to add 63 instead, since a double negative is a positive, and we're taking away the c. Now the c's cancel out, so our answer is going to be 63. That means that the area under the curve, 5x squared, plus 2x plus 9, the area is 63 in between 0 and -3. And one last thing, let's say underneath the curve. The area underneath the curve can go on forever. So the limit to underneath the curve is the x-axis. So really, it's the area between the line and the x-axis in between those two values. With trigonometry, you might have heard the mnemonic, so, ka, toa. And notice how I wrote SOHCAHTOA from left to right, but I put the middle letter of each section slightly raised in a triangle. So an important thing to mention before we start is that to use this type of trigonometry, we have to have right-angled triangles. We will look at some non-right-angled triangles later on this slide. All the triangles have got right angles. Now we can label the sides of these triangles depending on where the angle is. Now, what I mean by where the angle is, well, there's 3 angles in a triangle. One of the angles in each triangle is labelled, it's the 90 degrees. Out of the other 2, we are only going to label one of the other angles. It doesn't matter which of the 2 we label, but with this kind of trigonometry, we're not interested in the 3 different angles in the triangle, only 2 of them. Now, we can give the different sides of the triangle names. So, for example, the hypotenuse is the longest side in the triangle. I'm going to label the hypotenuse on each diagram. Now, if it's not really clear which the longest side is, another clue for the hypotenuse is that it's opposite the right angle. So no part of the line that makes up the hypotenuse touches the right angle. That's why we call it the opposite. Now, what about the other sides? So one side is called the adjacent. Now, the adjacent side is the side where the line that makes it up touches both angles. So you can see we've got the right angle next to the adjacent and the labelled angle next to the adjacent. And we don't care about the third angle in the triangle. We're not including that in this definition. So we say it's adjacent to the angles. It's the 2 that are labelled. You can't be next to all 3 of them. So if we have the same angle labelled in each triangle, and again, where this angle is important because if it's the other one, then the adjacent will be in a different position. But if it's at the bottom right in this kind of triangle, then the adjacent is always going to be in the same place. The last side we call the opposite. Now, if you memorize 2 of these definitions, the third one's just the other side. So we could just label all these opposites straight away without thinking about it, because there's only one side left. But the definition of the opposite is that it's opposite the labelled angle. Now, we're not talking about the angle that doesn't have a label. We're not talking about the right angle. We are talking about the angle at the other side of the triangle that's labelled. So no part of the line that makes up the opposite is touching that angle. The next thing is you're only going to be given 2 of these as clues in these questions. So if you're working with the solar form of the triangle, you see an O and a H in there. That means we're using the opposite and the hypotenuse. So we don't need the adjacent. If you're using the car form of the triangle, you'll see A and H in there. That means we're not going to use the opposite. And finally, you see the TOA form of the triangle, you'll see O and A in it. That means we're using the opposite in the adjacent. So we're not using the hypotenuse. And in each triangle, while we can see two letters that correspond to something that we know, opposite, hypotenuse, or adjacent, what about the S, the C, and the T? Well, these are our trigonometry words that we're using. So we have sine, cosine, and tangent. And these always refer to the angle. So you've got O and H, then the angle is going to be referring to sine. If you have H and A, the angle is referring to cosine. And if you have O and A, the angle is referring to tangent. So actually we end up with 3 items of interest in the triangle, depending on which form of triangle we're using. 2 sides and an angle. And so now we've gone through the first bit of trigonometry that's really important, which is the labeling of the triangles and then selecting the correct form of the triangle based on that. So it might be a bit confusing. I've gone through 4 different triangles at once, but it's on purpose. You label the triangles and you select your form of the triangle. One last detail with this, if we're writing these out in formulas and we don't really have a way to refer to the angles. So we're going to call the angles theta. Now theta is a Greek letter. It looks like a 0, but it's got like a curvy bit in the middle. Again, it's a 0 with a curvy line through the middle. So whenever I say theta, I'm talking about the angle. So let's have a look at our first triangle. Now, what's going to happen is that out of the 3 different letters we've got here, the O, the H, and the theta, you'll be given 2 of them, and 1 of them will be missing. So we're going to look at missing sides first. So what if you are looking for the length of the opposite, and you're given the hypotenuse and the angle theta as clues? What do you do? Well, we'll look at the form of the triangle. We cover O up with our finger and we'll look at what's left. If you cover O up with your finger, you'll see S and H next to each other. Now, if you've got 2 things next to each other in the form of a triangle, that means you are multiplying them together. You cover up O and you've got S times H. That means the opposite will be sine theta multiplied by the hypotenuse. Now, you will need a calculator for this. So on your calculator, you'll press the sine button, a bracket will open. You type in the angle, you close the bracket, and then you multiply by the length of the hypotenuse. That will give you the length of the opposite. Now, let's say you want to find a different side. Let's say you want to find the hypotenuse. So we'd have a value for the opposite, we have a value for the angle. So we look again at the form of the pyramid for this. We're looking for H, the hypotenuse. So you cover it up with your finger. If you cover H up with your finger, you'll see the O is above the S. Now, if the letters are above each other, that means you are dividing them. You're going to write them as a fraction. So you got O over S. So that means that you take the opposite and you are going to divide it by sine theta. Alternatively, you could write it as a fraction and write O over sine theta. But for space issues, I will write it as a division for this bit of revision. So you get your calculator, you will type the value of the opposite in, you will type the divide symbol, then you press the sine button, your bracket would open, and you type in the size of the angle and close the bracket. And that will give you the length of the hypotenuse. So now let's move on to the next triangle, the one underneath. Now this one has got H and A labelled. The only form of the triangle with H and A in it is the cosine triangle. So that's the one we're going to use. I'm going to imagine what happens when we're looking for the adjacent and what happens when we're looking for the hypotenuse. So if you're looking for the adjacent, you cover it up with your finger. And what you see in the form of the triangle is C times H. So you would do cos theta multiplied by the hypotenuse, and that will give you the length of the adjacent. If you're looking for the hypotenuse, you cover the hypotenuse up with your finger and you see A over C. That means you're going to do A divided by C, and C being cos theta. So now we're saying S, C, or T, as well as using the button on the calculator for the trigonometry word sine, cos, or tan, you're also putting in the angle theta. Looking at the one underneath, this one's got O and A labelled. There's no hypotenuse for this one. The only one that doesn't have a hypotenuse, that has O and A instead, is the tangent. We're going to imagine looking for the adjacent and the opposite. If you're looking for the adjacent, you cover up the A in the tangent form of the pyramid. And if you do that, you've got O on top of T. That means you're doing the opposite divided by the tangent. If you're looking for the opposite instead, you cover up the O and you see T times A left over, which is going to be the tangent multiplied by the adjacent. So I've written down 6 formulas here. Now you do not need to remember the 6 formulas. These can all be derived from the formula triangles. but I just want to show you the kind of maths you're going to be doing. And essentially, it's just figuring out if you are multiplying or dividing the two numbers that you're given. Again, being really clear with the angles, you don't type in a number for the angle without a sin, cos, or tan. So we've looked at missing sides. What about missing angles? What we want to find what theta is. In our first triangle, we've got O and H, and we've got theta. So this means it's going to be a sine form of triangle. Now, if you're looking for what theta is, what the angle is, you cover up the trigonometry word. So we're going to cover up sine. And if you cover up sine, you get O over H. So we're going to take the opposite and we're going to divide it by the hypotenuse. Now, there's a problem here. We have to use a trigonometry word. We have to use sin, cos, and tan because they look up what the answers are depending on which set of clues you've got. So we need to include that somehow. So we're saying really that sine theta is equal to the opposite over the hypotenuse. Now that's the correct formula, but it gets us sine theta. It doesn't get us theta on its own. So how can we get theta from doing the opposite divided by the hypotenuse? Well, if you think about solving equations, what we want to do is do the opposite of sine to both sides to get theta on its own. And we can do that to say that theta is going to be equal to the opposite of sine done to the opposite divided by the hypotenuse. And there is a button on your calculator to do the opposite of sine. It's labelled sine -1. It could even be maybe labelled arc sine, but sine -1 is the most common, and it's going to do the opposite of sine for you to rearrange the equation and get you the correct answer. Moving on to the same thing with cosine. If you cover up the c, you have a over h. So if you cover up the c, which corresponds to cos theta, then we see that that's equal to the adjacent divided by the hypotenuse. So if you just want theta on its own, not cos theta, you need to do the opposite of cos to both sides. That's going to be cos -1 done to the answer to a over h. And you can either type all that in your calculator all at once. So you can press cos -1, usually shift and pause will get you that. It'll open a bracket. You type in a divided by h, and then you close your bracket, and you get your answer in one go. Alternatively, you could do a divided by h, get an answer, and then you could cos -1 that number. Finally, it's the same thing with tan. If you cover up tan theta in your formula triangle, what's left over is O over A. And so it would be tan -1 to both sides. That'll give us that theta is equal to tan -1 O divided by A. Altogether, we've got 9 different formulas, but you don't need to remember all of them. All you need to remember is SOHCAHTOA, because the order in which you write them, if you put them into formula triangles and then you cover up the thing you're looking for, will actually lead you to all 9 formulas when you need. Now, all the triangles so far have had right angles in them, but what if we don't have a right angle? So we think about Pythagoras Theorem uses right angles. SOHCAHTOA with trigonometry uses right angles. So we're going to look at how you do those things without right angles. Another thing with triangles that uses right angles is when you find the area of a triangle, because you do base times height divided by 2. The base and the height are at right angles to each other. So we're going to look at an alternative for finding the area, doing Pythagoras Theorem and doing trigonometry without right angles. Now, the first thing with this is called the sine rule. Now, here's how we label our triangle. So we're going to label the angles with capital letters. We're going to have angle A, we're going to have angle B, and we're going to have angle C. Then we're going to label the sides with the lowercase letters. We have side A, side B, and side C. Now, why have I done it this way around? Well, what you'll notice with this is that the letters are opposite each other. So the capital B for angle B is opposite the lowercase b for side B. You'll notice the capital A for angle A is opposite the lowercase a for side A. That means that no part of side A is touching angle A. And the same thing with the uppercase angle C being opposite the lowercase side C. So what does all this mean? Well, all these fit a certain ratio we can use to solve the problem. So what we say is side A divided by angle A, and it's a sine of angle A, it's called the sine rule, is the same as side A divided by the sine of angle B, which is equal to side C divided by the sine of angle C. Now, out of this ratio, you're only ever going to have 2 of these. So whichever 2 you have are the 2 that you're going to use. There's one more detail with this, which is it doesn't matter which way around the numerators or the denominators are. So I'm just going to label it with a little arrow. Now, you're going to be consistent with this. You can't have a mix of sides on top and angles on top. It's got to be all the sides are on top like in this example, or you flip it around and all the angles are on top. And you'll find doing it different ways around will help depending on if you're trying to find a side or a missing angle. Generally, you want the thing you're looking for on top. So the version that I've written is going to be the version you're going to write when you want to find a side. Now, the next rule is labelled the same way. So we're going to label our angles with capital letters A, B, and C. And we'll label the sides with lowercase A, B, and C, with again the equivalent letters to each other being at opposites. Now, this is a version of Pythagoras Theorem. We don't have a right angle triangle, and the formula actually starts off with Pythagoras Theorem. So we say that A squared is equal to B squared plus C squared, but then we make an adjustment because we don't have a right angle, and we take away 2BC cos A, and that makes the adjustment for not having a right angle. And make sure you get the lowercase and uppercase A is correct. Uppercase is an angle, of course it goes with cos, and lowercase is going to be a side. Now, because you label which ones are A, B, and C, the actual order of the letter doesn't matter. So you could have the same formula for B squared and C squared. It's just that, if you're looking for B squared, that's going to be A squared plus C squared. Looking for C squared, it's going to be A squared plus B squared. It's the two that you don't have. And the takeaway is also two lots of the two letters that you're not looking for. Because, of course, you have values for these. Then if you're looking for B, then it's going to be cos B at the end. Then you're looking for C, it's going to be cos C at the end. Now, these two triangles are labelled the same way, so which formulas do you use? Well, it's all about the number of clues you're given. So if you're going to use the sine rule, then with the sine rule, you'll see that each section has one side and one angle. So essentially, you need multiple angles for the sine rule. So if there are two angles in the question, and two sides, you're going to use sine rule. If there's only one angle in the question, then you're going to use cos rule. When I say angle in the question, you might not be given the angle. So it might be, the angle's labeled as X, or it's labeled as A or theta. So when I say you need an angle, I'm not saying you need the value for it. It just needs to be involved in the question. So two sides, two angles, use sine rule. Three sides, one angle, then you're going to use cos rule. And if for some reason you've got three angles, then there's no way to find the sides from three angles because angles don't scale up with sides. The last thing we're going to look at is the area of a triangle without a right angle. And again, the labeling is going to be consistent with the previous two. So we're going to label the angles A, B, and C, and label the sides that are opposite A, B, and C, with the same letters being opposite each other. So to find the area, what you do is you do half of, let's label this with, let's just write area as a full word. It's half of A times B, which is very much like the triangle formula, half of the base times the height. Because A and B aren't at right angles to each other, we need to make an adjustment, and the adjustment is sine C. And like the previous example, because we've labelled A, B, and C, we can write different versions of this formula, but it's basically two sides and the angle of the third side. We could write it as half BC sine A. You can see all three letters are present, A, B, and C. It's just that one of them is uppercase for the angle. And we could also write it as half AC. So we've used up A and C, so then the adjustment is going to be involving the other one, which is B. So there we've got all the various trigonometry formulas. We have got 6 formulas to use to find missing sides and angles with a right angle. And if you consider the area of the triangle formula and the Pythagoras Theorem formula for missing sides, then we've got 3 formulas we can use with triangles that aren't right angled. The sine rule, if you've got 2 sides and 2 angles, if you're finding a missing side or angle. The cosine rule, if you've got 3 sides and 1 angle, and you're finding a missing side or angle. And finally, we've got a formula for the area if you don't have a right angle. Trigonometric graphs show the ratio between sides in triangles depending on which 2 sides you're looking at. And it all goes back to think about the SOHCAHTOA. So if so, we've got O and H. So this graph shows that as an angle goes through different values, it shows a ratio between the opposite and the hypotenuse. We also have negative values. Now, these normally aren't possible in triangles. So what these refer to is if you have a triangle on a kind of coordinate grid and one corner is at 0, 0, then you could have kind of reverse triangles, which theoretically might have a negative measurement, but really the triangles reflect in the opposite direction. So for example, all the positive values could be a triangle that quick sketch looks like this. Whereas the negative values could be a triangle that's reflected that looks like this. So when you're using these for real life objects, you just ignore the negative numbers. Negative numbers are just referring to the rotation or the reflections of the triangle. Now you've got the adjacent and the hypotenuse, then the ratio has the same pattern as sine, but it's all shifted. So you can see we've got the same kind of peaks and troughs. They're just happening further along. It's all shifted by 90 degrees. So cosine starts at 1, 90 degrees after sine starts at 1. The sine's at 1 at 90 degrees, cos is at 1 at 0. So that's that 90 degree shift. Tan's a little bit different. It's the ratio of the opposite and the adjacent. Now it rapidly increases and it actually goes past 1. And this is going to continue up and up and up and up and up to a little sketch. Now, what is this dotted line that's next to it? And this dotted line means that you cannot have a triangle that compares the opposite and the adjacent at 90 degrees, because that's going to be an impossible angle to draw. So when we say the graph's going up and up and up and up and up, what's going to happen is it's never going to touch this green line. It'll get infinitely close to the green line, but it will never touch the green line. Now, it normally kind of cuts it off at 1, but it might be useful going up to 2 sometimes as well. And then what happens is, after 90 degrees, tan resets, and it starts infinitely close, and then by the time you get to 135 degrees, it starts to show up back on the graph. But again, this line's going to do the same thing as we get infinitely close to the next dotted line. I've got a name for these dotted lines. We call them asymptotes. So it's a place on the graph with impossible values. And you do need to show it on the graph. The graph will be wrong if you have to sketch it and you don't show the asymptotes. Very important that it's known that you can't go through those values, which on this graph is 90 and 270. And they're 180 apart. But what you'll find with all three of these graphs is they can continue infinitely on forever. So we're only looking at a snapshot of the graph, the most useful part of a graph, in between 0 and 360. Another thing to mention is that these graphs all show values in degrees. And degrees is when you split a circle up into 360 degrees, which we mentioned with the geometry revision that it's 360 degrees. It's got a lot of different factors you can divide it by. It's been chosen by a person in the distant past as a good number to use. There's no particular mathematical reason why it's 360 other than it being easy to divide it up. Whereas a lot of maths kind of like comes out of kind of like universal rules with the universe. So it's kind of like we kind of don't want to just choose a random number. We want to base it on something. So there's another way to measure these graphs, and it's called radians. But basically, radians is rather than cutting a circle up into 360 degrees, in radians, you're going to cut the circle up into 2 pi degrees. And so because pi is a number that comes out of calculations with circles, and we're dividing up a circle, that it seems like an appropriate thing to use. And using 2 pi does make some equations in some contexts easier to use. So what we're going to look at now, important values on all three of these graphs. So we'll look at important values on the sine graph, the cosine graph, and the tangent graph. Now, the first important value is where we start, and we start at 0 degrees. And in radians, we just call that 0 radians. So on the sine graph, you can see at 0, we're at 0. I'm just going to highlight it on the graph. On the cos graph, we start at 1, and on the tan graph, we start at 0. This is the first important set of values. Now, if you type sin 0 into your calculator, you'll get 0. If you type cos 0 into your calculator, you'll get 1. But you might get this as a non-calculator question, and you might need to memorize these values. Also, if you have to sketch the graph, it's important to know these so you know where to start drawing it. Particularly with sin and cos, which are the same graph shifted along. So it's important to know that cos starts at 1. The next important value is at 30 degrees. In radians, we call this pi divided by 6. And that corresponds to the same part of the circle as 30 degrees. Now, on the sine graph, if you look at 30 degrees, so these graphs go up in 15s. So you can see that if we go across 2 lots of 15, which is 30, we're halfway up. So the value is a half. On the cos graph, at the same point, halfway up, we're nowhere near 30 degrees. So actually, when we look at 2 squares across, it's actually quite close to 1, isn't it? Now, there is an exact value for this, and we call it root 3 divided by 2. So we can't get like a whole number, integer whole number. It is an irrational number, but it is something we can display without any decimal places by saying √3/2. So we call it an exact value. And with tan at the same part of the graph, again, you know, we're a distance up the graph. That's got an exact value. It's 1/√3. The next important value is 45 degrees. So that's 3 rectangles across on the diagram. You can see it labelled. And for sine, you can see it's up here. And for sine, that's going to be 1/√2. On the cos graph, you can see it's also got an odd value. And that's going to be also 1/√2. So that's a point where both sine and cos have the same value, although sine's going up at that point and cos is going down. And then on the tan graph, if we go 3 across, you can see that's where it hits 1. I should mention that in radians, 45 degrees is pi divided by 4. Next, we'll look at 60 degrees. So 60 degrees, in radians, that's pi divided by 3. On the sine graph, it's √3/2. On the cos graph, it's a half. And on the tan graph, it's √3. Now notice how the sin and cos values, √3/2 and a half, are the reverse or the same at 30 degrees. So it kind of shows that, you know, sine and cos are similar graphs. They're going to hit the same values. They're the same graphs just shifted along. Tan, of course, is going to give you something that is completely different. The last important value is at 90 degrees. Call that pi divided by 2. So 180 degrees will be pi, and 360 is 2 pi. And on this one, sine is 1, cos is 0, and tan is where we have an asymptote. So 90 degrees for tan is an impossible value. It's something that we can't have. So we're not going to write down an answer for it. A good way to write down what tan 90 is to say that it's undefined. Now, one last thing we can do with these graphs is use them to make predictions. So, for example, if you want to know what sine of 30 degrees is without a calculator, then you can go to the graph, you can find where 30 degrees is, you can draw a line up from 30 degrees, and you can draw a line across, and you can see that 30 degrees is equal to a half. And so you can write the answer a half in. That's the first thing you can do. Now, the second thing we can do is the inverse calculations. So let's say we wanted to do, let's do cos for this one. Let's say we wanted the value of inverse cos to a half. So this time, rather than finding 30 on the x-axis and going up and across, we're going to find a half on the y-axis and go across and down. So you find a half, you go across, you go down, and we can see that 1/2 on cos corresponds to 60 degrees. So we could write 60 degrees as our answer. Okay. But here's a weird thing. What if we continue going across at a half? We end up getting another value. And we go down from here, we can see it's 15 below 315. So this is 300. So we can see that cos to the -1/2 is 60, and it's 300 degrees. And as I said, these graphs do go on forever. We've only got a 0 to 360 snapshot here. So you would have more values than this. So the important thing here is that when you're going from an angle to a number, you are going to get a single answer. If you are going from a number to an angle, you will get an infinite number of answers. So what we need to do is restrict the range of these answers. And so, for example, for these graphs, got sin x, cos x, and tan x, we would say that x is in between 0 and 360. And so we can write out like this. And that's true for all 3 of these graphs. So if you get a question and it says the range of values is in between 0 and 360 with this confusing looking notation here, all that means is that there's infinite answers and you only want the answers in between 0 degrees and 360 degrees. And you might see different ranges. You might see -180 to +180, for example, or you can see ranges written in radians. And you'll know it's radians because it will have pi written as part of the angle. So one last thing to look at is a prediction with tan. So let's do tan to -1 of 0. Now, when we look at our table, we've got this value in already. Tan 0 is when we're at 0 degrees. So we can write 0 degrees in straight away as one of the fixed values that we know, one of the exact values. We look at the graph. If we start at 0 and work our way across, we can see we've got 0 degrees. Tan graph also meets that point at 180 And it also meets that point at 360. So actually, tan 0 degrees and 180 degrees and 360 degrees. So we've got 3 different answers. So then going back to our table of exact values, you can also find multiples of these values within the graphs by looking at the kind of symmetry of the graphs. So for example, sin 30 being a half, there'd also be another half. There's a half 30 degrees after 0. When the graph repeats, there'll be another half 30 degrees after 360. So sin 390 is also a half. So also expect to find multiples of these values. Now, these are linked to 90. You can see with the sine graph in particular, the second part of it is negative. So if you think then sine a half being at 30 degrees is 30 after 0 when it crosses through the x-axis. It crosses through the x-axis at 180. So what's 30 after that? Well, it's going to be 210. And you'll see at 210, there's going to be a negative version of a half there. And so you get negative a half on the graph. So there's way more exact values in these. You just have to use the symmetry of the graphs to find the rest of them, as you can see with tan minus 1 and cos minus 1 over half and 0 respectively. With trigonometric equations, we're going to use trigonometric graphs to help us solve equations. So let's have a look at 3 types of equations. So the first type is you might have something like sine theta, and then we're adding or taking away something from it. So for example, it could be taking away 20 degrees from it. And that's equal to 0.37. So how do we solve the equation? Well, we want to get theta on its own. So our first step is doing sine to the minus 1 to both sides. And that will leave us with theta minus 20 degrees is equal to, if you do sine minus 1 to 0.37, you're going to get 21.7 to 1 decimal place. So I have rounded this. So we've converted 0.37 into an angle. The last thing we need to do is add 20 degrees to both sides, which will leave us with theta is equal to 41.7 degrees. And it looks like we managed to get the answer without actually using the graph. But there is an issue here. And the issue is with the step we did inverse sine 0.37. Now that gives us 21.7 degrees. Let's try and find it on the graph. So 0.37, the graph goes up in sets of 0.2. So 0.37 is going to be just below 4, so around about here. We go across from there and we go down, then this is where we're getting the 21.7 degrees from. But this isn't going to be the only answer. There is another answer, because if we continue that line onwards, it's going to hit another point of the graph and give us another answer. And the unfortunate thing here is the graph is so complicated that we can't really read off an accurate answer here. We know it's going to be somewhere in between 135 and 180. We could narrow it down a little bit more, but we don't know the exact angle. Or do we? Because we can use the symmetry of the graph to get the exact angle. Now, what we're looking at with the symmetry of the graph is that the part where we got our first answer was 21.7 away from 0. These graphs are symmetrical, and there is a line of symmetry going through the peak if we only look at the first 180 degrees. So we're not looking at the second half of the graph. So if our first answer is 21.7 degrees away from where the curve starts to rise, looking at the symmetry, our other answer is going to be 21.7 degrees away from the end of the curve. And where does it end? It ends at 180 degrees. So we do take away 21.7 degrees, and that gives us our second answer. And it gives us 158.3 degrees. So using the graph, we've now come up with a second answer. Theta is equal to 41 degrees, and theta is also equal to 158.3 degrees. Now there's one more difficulty, and that is that's the value of theta. And what did we do? Well, we added 20 to it to get our final answers. So actually, what we need to do now is add 20 to it as well. So a proper answer is going to be 178.3 degrees. So it's important to know at which point that second answer comes in. So look at the symmetry with the 21.7, then it comes in at the same place as the 21.7, which was halfway through our working out. The second type you might find, rather than adding or taking something onto theta, with our next question, we're going to have cos of theta, but we're going to multiply it by 3 and have cos of 3 theta. And that's going to equal negative 0.77. So again, we follow the same process, and we're going to try and get rid of the cos first and get theta on its own. We need to do inverse cos to both sides. That gives us 3 theta is equal to the inverse cos of negative 0.77. That gives us 140.4 degrees to 1 decimal place. Then we need to divide both sides by 3 to get theta on its own. And so if I just take the entire number, so I'm not rounding it here, I'm just using the full number of characters on the screen, I'm now going to get 46.8 degrees to 1 decimal place. So we've got a single answer by solving the equation, but again, we're going to need the graphs here because we're going to find a second answer, at least a second answer. So we go to our graph and we're looking at the negative 0.77. So if it's going down in 0.2s, that's going to be just under 0.8. So we're going to look across. Don't worry about being too accurate with this. We'll look across. We hit the line. We go up. And we're hitting just after 135, which is about right because that should be the 140.4. Now, what we're looking for here again are multiple answers. So we go across from the 177. We're going to hit our second answer. Then we can go up. And we know roughly where the second answer is going to be. So what we need to do now is think about the symmetry of this graph and how we can approach this problem. Now, the sine graph, the symmetry, only really applied to the first half when we're kind of looking at the x-axis. With the cos graph, we can put the symmetry right down through the middle because the entire graph is symmetrical. So then looking at the symmetry, our first answer is 140.4 away from the first side, which starts at 0. So with a symmetry, we're going to be 140.4 away from the opposite side. Now, the 140.4, we're starting from 0. Going the other direction, we're starting from 360. So we do 360, take away 140.4, and we're going to get our answer. And it's 219.6 degrees. Now, again, that's rounding to 1 decimal place. We're going to do something else to it. So we want a higher level of accuracy. So what I'm going to do is, I'm going to, on the calculator, do inverse cos negative 0.77. Get the full level of decimal places. It's 140.353889. I'm going to take that number away from 360. Now, with that number, remember, this comes in at the 3 theta section. It corresponds to 140.4. So what I need to do now is divide my full level of accuracy number by 3, and that gives me 73.2 degrees. So now using the diagram, we have 2 answers. So we solve the equation to get one answer, and then we use a symmetry of the graph to get our second answer, with each graph having a slightly different symmetry. Now there's a third step. Now the trick here is the range of possible answers. Now for these questions, we're going to have a range in between 0 degrees and 360 degrees. Now, if we're dividing by 3, you can see our 2 answers are quite close together. And if you divide by 3, you can make quite large numbers fit into the 0 to 360 range. So what we want to do really is we want to look at a 0 to a 3 times higher range just in case. So 360 times 3 gives us 1080. So when we find answers in that range, after we divide by 3, they're guaranteed to be in between 0 and 360. And our graph only covers in between 0 and 360. So how do we get the rest of the answers? Well, another part of the symmetry of these graphs is that they repeat every 360 degrees. That means that if you add 360 degrees onto your answer, it's going to correspond to the answer on the next section of the graph if we continue drawing it further out, perhaps up to 720 for another 360, and up to 1080 for another 360 on top of that. So the graph repeats every 360 degrees. So if we are dividing by 3, 360 divided by 3 is 120. So this pattern is going to repeat every 120 degrees. So going from a 360 repeat to a 120 repeat because we're dividing by 3. That means we can add 120 onto our answer for another set of answers. We can take 46.8 and add 120 to it, and we get 166.8. We can take 73.2 and add 120 to that, and that's going to give us 193.2 degrees. Notice how these answers are still within the 0 to 360 range. Now, we can divide it by 3, so rather than repeating once within 360, the 120 is going to repeat 3 times. Let's add on another 120. So 166.8 plus 120 gives us 286.8 degrees. And 193.2 plus 120 gives us 313.2 degrees. Again, the answer is still under 360. Now, if we added another 120 to that, we're going to get 433.2, and that is outside of our range. So when you have a question like this, where you are dividing, you also need to multiply out your range by what you're dividing by, because that division is going to fit more numbers within that range. Remember that these graphs repeat every 360 degrees. So if you divide it, it's going to repeat by whatever you divided by. In this case, repeat every 120 degrees. It's also worth noting this was a 3 theta question. You can also have fractions in there. So, rather than multiplying by 3, you might have one where it's a half theta, which means that you're dividing it by 2. That means that to solve the equation, you'll be multiplying rather than dividing. And that will have the opposite effect. And that will mean you might have less answers. And some of your answers might end up falling outside your range after you multiply them. So always make sure that any numbers that aren't in your range, you delete, you don't use. Now, the last thing we'll look at is something like this, where we have 5 tan theta equals 2. So in this case, what we're doing is we're multiplying the entire thing by 5, not just theta. All of tan theta has been multiplied by 5. Now, to rearrange this, the first step is divide both sides by 5, and that will give you tan theta is equal to 2 divided by 5, 2/5, which is equal to 0.4. So it's actually not too hard to get rid of any numbers at the start. You just divide 3 by it, and then you've got something that looks like a normal question. So all we need to do now is do inverse tan to both sides, and that will give us that theta is equal to the inverse tan of 0.4. Or inside your brackets, you could write 2 divided by 5. That would work as well. And that gives you 21.8 degrees to 1 decimal place. Now, again, like all of these questions, this is going to give you something that's one of multiple answers. So let's look at tan 0.4. So you see we're coming in and we're getting 21.8 out of it. However, if we extend this line, we can see that there is going to be a second answer. So how do we get the second answer? Well, you're surprised now with tan, it's really easy. Now, the symmetry with sin, you can see, we just look at the 180 degrees of sin, the first 180, and we put the symmetry line through the peak, and we do 180 takeaway. With cos, we can put the line of symmetry through the middle of the entire thing, and we do 360 takeaway. Now, with tan actually doesn't repeat every 360 degrees. Well, it does in a way, but it also repeats every 180 degrees. Now, that's a factor of 360, so it will repeat every 360 as well, but it's also got a shorter repeat like this. That means we can just add 180 onto our answer. So we take a 21.8, we can add 180 onto it, and that will give us that second answer. So we're doing 180 plus the 21.8, and that gives us 201.8 degrees, which is our second answer. Now, as an extra, what if the range of this isn't the 0 degrees to 180 degrees that the previous 2 questions have been? What if this one is negative 180 degrees between x and positive 180 degrees? Well, in this situation, our answer we just got is outside of the range. We can't use the answer. It's bigger than 180. And our graph doesn't show the negative part of tan. So do we need to extend the graph? Well, we don't, because we know it repeats every 180. So as well as adding 180 to get larger answers, we could actually take away 180 as well. And the 21.8 take away 180 is going to give us negative 158.2 degrees. And that does fit within the range. So once you've got your final answers, always go back, look at the range of answers you're allowed and see if your answers fit within it. If any are outside, cross them out. And if the range goes into negatives you didn't expect, then just check to see if there are any in the other direction, again, using the symmetry you've been using all along. We are going to have a look at trigonometric identities. Now, with trigonometric equations, we've always had one of sin, cos, or tan. We'll look at here what happens if we have more than one of them. And then identity means we've got a kind of formula that will help us reduce the multiple copies into one copy, so we can solve it as normal. So for our first one, we're going to have a look at the equation 6 sine squared theta plus 5 sine theta plus 1 is equal to 0. So with this, what's happening is we have got two lots of sine. And hopefully you notice that it looks like a quadratic equation. So we're going to treat it like a quadratic equation. So we need to open up some double brackets and we need to factorize this. Now we're not using x like we normally would, we're using sine squared. So we need sine on both sides because sine theta times sine theta will give us sine squared theta. Just like x times x will give us x squared. It works the same way. And for factorizing a quadratic, we want to find two numbers which multiply together to make 1. And add together to make 5. Which numbers multiply to make 1? Well, it's got to be 1. And then how do we make those make 5? Well, 1 and 1 can't make 5. But remember with this, because we have these 6 on the sine squared, then we can use those to multiply our coefficients. So let's say 6 is made of 3 times 2. When you multiply these brackets, you get 3 times 1 is going to be 3 sine theta. And you're going to get a 2 sine theta times 1 is 2 sine theta, and 3 sine theta and 2 sine theta will add together to make 5 sine theta. So I've rushed through how to factorize a quadratic. Again, always the same way. So go and look at the revision for factorizing quadratics for a bit more information. But anyway, we've factorized it, and now we need to make the brackets equal to 0. Now, if we want to make the first bracket equal to 0, then sine theta would have to be a third, or rather a negative third, because 3 times negative third will give us negative 1, and negative 1 plus 1 will give us 0. So our first answer is going to be that sine theta could be a negative third. To make the second bracket be equal to 0, then that sine theta would have to be equal to negative a half, because two lots of negative half will give us negative 1, and negative 1 plus 1 will give us the 0. So now we've got two answers, and we've now got two equations. And then we actually carry on like we've done with trigonometric equations. So we want to get theta on its own. So we need to do the inverse of theta to both sides, the inverse of sine to both sides. We take inverse sine and negative a third. That will give us negative 19.5 degrees. And if we take the inverse sine to get theta on its own of negative a half, that will give us negative 30 degrees. So we've got two answers. We need to check the graph for the rest of the answers. It's also worth noting the range we're looking for. Now, what if the range was only in between 0 degrees and 360 degrees? We are allowed either of the two answers we've been given. So what do we do? Well, firstly, you would sketch your sine curve. And you just need to sketch the positive one between 0 and 360. And we look where negative 30 is first. Negative 30 is going to be starting, and we can extend this slightly into the negative with a little sketch. So negative 30 is going to be roughly around about here. And we can see there's going to be another answer after 180. And there's going to be another answer before 360. Now, because the negative 30 that we've got is 30 away from 0, we know there's going to be symmetry involving 30s here. And what's going to happen with our other two answers, let's just do these in another colour actually, is that we're going to have one that's 30 above 180, which is going to be 210. And we're going to have one that's 30 below 360, which is 330. So while we're not allowed to have negative 30, using the symmetry of the graph, we can see it's going to correspond to 210 and 330 degrees. That's our first one done. Now, for the next one, it's very close to negative 30. It's at negative 19.5. Now, that means we're going to follow the same method. We're 19.5 away from 0. We're going to be 19.5 away from 180 and 360. So we take 180 and add 19.5, and that will give us our second answer, which is 199.5. Then we're going to take 360 and take away 19.5, and that'll give us our fourth answer, which is 340.5. So again, while our range of answers doesn't allow negative 19.5, we can use the symmetry of a sine curve to work out where the positive versions would be. And it's 199.5 and it's 340.5 degrees. And so there we have our 4 answers for theta. So that's how you get rid of having 2 sins or 2 cos or 2 tan. And it worked the same way for cos and tan as well, if it was a cos or tan squared. Now, what if we had a mix of sin and cos? So for our next question, we are going to have cos theta multiplied by cos 2 theta plus sine theta multiplied by sine 2 theta. And that's going to equal negative 0.43. So that looks like a mess. How can we solve that? Well, this is where we're going to look at our trigonometric identities. Now, there's 3 we need to look at, and these are called the compound angle formulas. So we have sine angle A plus or minus angle B is equal to sine A times sine B, or rather sine A times cos B, plus or minus cos A times sine B. So if you've got a really long thing with lots of sines and coses in, you can compress it down into just a sine. The second formula, which is the one we're going to use for this question, is that cos A plus B is equal to cos A times cos B. Now, in our original, it's plus or minus. It's going to be minus or plus. So it means that if this is a minus, then we're just going to simplify it to a plus. And if this is a plus, we're going to simplify it to a minus. And on the other side, we've got sine A multiplied by sine B. There's also one for tan. So tan plus or minus B is equal to, and it's tan A plus or minus tan B all over, so we're dividing this, 1 plus or minus tan A tan B. And while these formulas look really complicated, that means it's going to be obvious that you've got to use one of them. So, we've got cos theta, cos 2 theta, plus sine theta, sine 2 theta. That looks really complicated. Obviously, we need one of these formulas. So we're going to use the cos formula. And with the cos formula, we've got to say what A and B are. A is the first angle we're mentioning. The first angle is theta. And B is the second angle we're mentioning, which is 2 theta. You can see we've got the cos theta, cos 2 theta, and the sine theta, sine 2 theta. So we've got those 2 angles being used. And we'll really carefully look at the plus or minus. Now, we've got a plus in our original. In the equation, it's minus plus and minus. It means we switch the sign. So this is going to be a minus. And cos theta minus 2 theta is going to be equal to 0.43. And we can actually do that sum. Cos theta take away 2 theta is going to give us negative theta. So it's 1 take away 2. So now we can do inverse cos to both sides to get negative theta. And the inverse cos of negative 0.43 gives us 115.5 degrees. So if that's negative theta, then positive theta is going to give us the opposite of that, which is negative 115.5 degrees. And so that is our first answer. Now, again, it's a negative and it's not going to fit on our graph. Now, you can sketch between 0 and 360, and then you can maybe extend the graph backwards, and that'd be one method of doing this. Another method is, why don't we do it with negative theta and then swap the signs on our final answers? So negative theta is 115.5. So let's find 115.5. So we had 0.43, so it's a negative 0.43, and then that corresponded to 115.5. So the second answer, we can look at the symmetry of the cos graph, is going to be here. We know the symmetry of a cos graph is going to be through the middle. So if we are going to be 115.5 away from the left-hand side, which is 0, we're also going to be 115.5 away from the right-hand side, which is 360. So 360 take away 115.5 will give us 244.5 as a second answer. However, these are negative answers, and the range is likely going to be between 0 and 360. So how do we get the positive versions of the answers? Well, remember, these graphs repeat every 360 degrees. All we need to do is add 360 onto the negative versions. So I'm just going to, for space, just adjust this. So negative theta is going to become positive theta. But if we do that, then we're going to have a negative 115.5 and a negative 244.5. So to get positive numbers out of these, all we need to do is add 360 to both of them. So we take the negative now, 115.5, and plus 360, and that gives us a positive 244.5. And if we take the negative 244.5 and we add on 360, that's going to give us a positive 155.5. So now I can adjust the answers again and get rid of those negative symbols. And a quirk of the cos graph is that positive and negative values, if you add on 360, when you've got two values like this, are going to correspond to each other. Now, the last question we'll look at is another way where we can mix together cos and sin. I'm going to look at cos theta is equal to 2.5 sine theta. And for this, we need to introduce another trigonometric identity. And for this one, it's going to be that sin divided by cos is equal to tan. So what we want to do is get the sin and cos to the same side. Let's divide both sides by sin. That will give us cos theta over sin theta is equal to 2.5. Now that is the opposite way around to the identity. Sin over cos is tan. We've got cos over sin. So to flip those around, what we're going to do is find the reciprocal of both sides. So to find the reciprocal of a fraction, you flip them upside down, which is what we've done, what we want for our identity. But then to do the same thing on the other side with the 2.5, you can't flip a whole number around or, something written as a mixed number. So what you need to do is 1 divided by 2.5. So again, we're taking the reciprocal of both sides. If it's a fraction, flip it over. If it's not a fraction, it's going to be 1 over the number. And we can do 1 over 2.5 is 0.4. And we can do sine theta divided by cos theta. It's tan theta. So tan theta is equal to 0.4. So once we have tan theta equals 0.4, we do inverse tan to both sides is equal to 21.8 degrees. All we need to do now is find the other answer. So we can see where 21.8 is. And then we can see that there's going to be another answer further on. Again, remember with tan graphs actually repeat every 180 degrees. So all we need to do is add on 180 for the other answer. So 21.8 plus 180 is going to give us 201.8 degrees. Now, there are more trigonometric identities in this, and we come into a lot more of these as we move on to a full A level. There's one more famous one that's going to be important to mention, and that is, we'll squeeze it in at the top, that sine squared theta plus cos squared theta is equal to 1. And you might see various rearrangements of that you've got to use to answer questions like this. But the gist of all three of these is there's different ways to have multiple trigonometric words, sin, cos, and tan. And there are things you can do to reduce them down to 1. Then you can use the appropriate graph to solve.
Ouch! This is why in some videos I have unexplained scratches.